Imagine a white dwarf, a cosmic ember, one of the universe's most intriguing leftovers from a star's long and luminous life. This small, incredibly dense object is the final, quiescent form of a star like our Sun. Though it is packed with a mass comparable to our star, it has been squeezed into a volume no larger than the Earth. It shines faintly, a ghost of its former self, slowly cooling over billions and billions of years, a diamond in the cosmic graveyard. A white dwarf is a marvel of stability, held together by a strange and powerful quantum mechanical force called electron degeneracy pressure. This is a force that arises from one of the most fundamental principles of the quantum world, the Pauli exclusion principle, which dictates that no two electrons can occupy the same quantum state in the same place at the same time. As the core of a dying star collapses under its own immense gravity, its electrons are forced closer and closer together into higher and higher energy states. This creates a powerful outward pressure, a quantum resistance to being squeezed that ultimately halts the gravitational collapse and holds the white dwarf up against its own weight. These stellar remnants are incredibly stable, some of the most reliable and predictable objects in the entire cosmos. But even they have their limits. And it is at these limits, at the very edge of stability, that some of the most profound and violent dramas of the universe unfold. This is where the Chandrasekhar limit comes into play, a critical tipping point discovered by the Indian-American astrophysicist Subrahmanyan Chandrasekhar. This limit defines the maximum mass that a white dwarf can have and still be supported by electron degeneracy pressure. That limit is about 1.4 times the mass of our Sun. If a white dwarf, through some cosmic circumstance, manages to accumulate more mass than this, if it crosses this critical threshold, it is in deep trouble. The inward pull of gravity will overwhelm the outward push of the quantum pressure, and the star will begin a new, catastrophic collapse. At this tipping point, the white dwarf is destined to become something even stranger, even more extreme. It might collapse into a neutron star, an object so dense that a single teaspoon of its matter would weigh billions of tons. Or, if it is massive enough, it might transform into the universe's ultimate monster, a black hole, a region of space-time where gravity is so strong that not even light can escape. But whether this collapsing star becomes a neutron star or a black hole, our current theories of physics are pushed to their breaking point. The moment of collapse is a place where the two great pillars of modern physics, Einstein's general theory of relativity and the theory of quantum mechanics, collide in a spectacular and, as yet, unresolved conflict. General relativity, our theory of the large scale, tells us that the collapsing matter should form a singularity, a point of infinite density and zero volume, where space-time itself is infinitely curved. But quantum mechanics, our theory of the small scale, tells us that the very concept of a point is meaningless, that the uncertainty principle should prevent such an infinite localization. To understand what truly happens at this ultimate frontier of reality, we need a new theory, a theory that can bridge the gap between the smooth, geometric world of Einstein and the fuzzy, probabilistic world of the quantum. We need a theory of quantum gravity. This is the holy grail of modern theoretical physics, the quest for a single, unified framework that can describe the universe at all scales, from the gentle dance of the planets to the violent heart of a collapsing star. In the 17th century, a scientific revolution began to unfold, a revolution that would forever change our understanding of the cosmos. Scientists and philosophers, driven by a deep and insatiable curiosity, started to ask big fundamental questions about the nature of space and time. They sought to peel back the veil of everyday experience and to glimpse the underlying mathematical order of the universe. The prevailing view at the time, the one that had been handed down from the great Greek philosopher Aristotle, was that of a dressed space, a space that was always filled with some kind of substance. The idea of a true empty vacuum was considered a logical absurdity. But a new generation of thinkers, armed with new mathematical tools and a new experimental spirit, began to challenge these long-held assumptions. Galileo Galilei, with his improved telescope, revealed a universe that was far vaster and more complex than the tidy, Earth-centered cosmos of the scholastics. His meticulous experiments on motion and mechanics laid the groundwork for a new, quantitative science of the physical world. And although he died in despair, his legacy was carried forward by a man who was born in the very same year of his death. Isaac Newton. In 1687, Newton published his monumental work, the Philosophiae Naturalis Principia Mathematica, a book that would become the foundation of classical physics for the next 2 centuries. In it, Newton laid out his 3 laws of motion and his law of universal gravitation, a single, elegant equation that described the force that governs the fall of an apple and the orbit of the moon. But to make this beautiful mathematical machinery work, Newton had to make a profound and deeply philosophical assumption. He had to assume the existence of an absolute space and an absolute time. For Newton, space was an infinite, eternal, and unchanging container, a fixed, 3-dimensional stage upon which the cosmic drama played out. And time was a universal, relentless clock, ticking at the same rate for all observers everywhere in the universe. This was the world of undressed space, a world where the void was real. In this classical, Newtonian view, if you were to remove all the matter and all the energy from the universe, this empty container of absolute space and time would still exist, a silent and eternal backdrop waiting for a new story to begin. This idea, while powerful and successful, raises deep philosophical questions. If the universe is everything that exists, how can it exist within something else? It is like trying to imagine a God's eye view of the cosmos, a perspective from outside of reality itself, a perspective that is, by its very nature, impossible for us to grasp. These are not just abstract philosophical games. They force us to examine the very foundations of our knowledge, to distinguish between what we can observe and what we must assume. We never truly see absolute space or absolute time. All motion is relative. An object is at rest only in relation to another object. The coordinate systems we use to map the world, the familiar X, Y, and Z axes, are entirely arbitrary human conventions. And yet, for Newton, the assumption of an absolute, unchanging framework was a necessary one. It was the only way he could make sense of concepts like acceleration and rotation. An object is accelerating not relative to another object, but relative to absolute space itself. But by the end of the 19th century, a new revolution was brewing, one that would challenge the very foundations of Newton's absolute universe. And it began not with gravity, but with the mysterious forces of electricity and magnetism. In the mid-19th century, a self-taught English scientist named Michael Faraday, a man with a little formal education but a profound and intuitive grasp of the physical world, began to unravel the deep and hidden connection between electricity and magnetism. Through a series of brilliant and simple experiments, he showed that a moving magnet could generate an electric current in a wire, and that an electric current could, in turn, create a magnetic field. These were 2 sides of the same fundamental coin. To describe these phenomena, Faraday, lacking the mathematical language of his contemporaries, developed a powerful and intuitive new concept, the field. He imagined space as being filled with invisible lines of force, a web of influence that stretched out from electric charges and magnets. An object doesn't just feel a force at a distance, it responds to the field at its location. Even Newton's theory of gravity could be rephrased in this language, with the Earth moving through the Sun's gravitational field. But it was Faraday's work on electricity and magnetism that truly established the field as a central concept in physics. It was a concept that would be given its definitive mathematical form by the brilliant Scottish physicist, James Clerk Maxwell. In a series of papers published in the 1860s, Maxwell synthesized all the known phenomena of electricity and magnetism into a single, elegant set of 4 equations. These equations revealed a deep and beautiful symmetry. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Maxwell realized that this interplay would create a self-sustaining, traveling wave of oscillating electric and magnetic fields, a wave that would propagate through space. And when he calculated the speed of this wave from the fundamental constants of his theory, he found a number that was astonishingly familiar, 300,000 kilometers per second, the speed of light. In a moment of profound insight, Maxwell realized that light itself is an electromagnetic wave. This was one of the greatest unifications in the history of science, a moment that revealed a deep and hidden connection between 2 seemingly disparate phenomena. But this triumph also created a new and profound puzzle. Waves, as they were understood at the time, always needed a medium to travel through. Sound waves travel through air, ocean waves travel through water. So, what was the medium for light waves? What was the ether that was waving physicists imagined a subtle, all-pervading, luminiferous ether that filled all of space and acted as the stationary, absolute reference frame against which the speed of light should be measured? But when scientists, like Albert Michelson and Edward Morley, conducted a series of incredibly precise experiments to try and detect the motion of the Earth through this ether, they found nothing. The speed of light was the same in all directions. Regardless of the Earth's motion, the ether did not seem to exist. This was a profound crisis for physics. Newton's laws seemed to require an absolute space. Maxwell's theory seemed to require a stationary ether, and experiments showed no evidence for either. The stage was set for a new revolution, a revolution that would be ignited by a young unknown patent clerk in Bern, Switzerland. In 1905, Albert Einstein, with a boldness and a clarity of thought that was breathtaking, cut through the confusion. He proposed that we should abandon the search for an ether and instead take the experimental results at face value. He elevated 2 simple principles to the status of fundamental postulates. First, the principle of relativity. The laws of physics are the same for all observers who are in uniform motion. There is no privileged, absolute state of rest. And second, the principle of the constancy of the speed of light. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these 2 seemingly simple postulates, Einstein deduced a series of profound and world-altering consequences. He showed that there can be no such thing as absolute simultaneity, that 2 events that appear to happen at the same time for one observer can happen at different times for another. This meant that there could be no absolute, universal time. Time itself is relative. He showed that for a moving observer, time runs slower and distances get shorter, a phenomenon known as time dilation and length contraction. And in a short addendum to his paper, published later that year, he showed that mass and energy are 2 different aspects of the same fundamental entity, linked by the most famous equation in all of science, E equals mc squared. The energy bound up in even a tiny amount of mass is immense. This is the equation that explains why the sun shines. And it is the equation that would later unleash the terrible power of the atomic bomb. Einstein's special theory of relativity was a stunning achievement, but it was incomplete. It dealt only with observers in uniform motion. It could not handle acceleration, and it was still incompatible with Newton's theory of gravity, which described a force that seemed to act instantaneously across vast distances. A clear violation of the new cosmic speed limit set by the speed of light. Einstein knew his revolution was only half finished. He would spend the next decade of his life grappling with the problem of gravity, a journey that would lead him to an even deeper and more beautiful understanding of the nature of space and time. The early 20th century was a time of unprecedented intellectual ferment, a period that saw not one, but two fundamental revolutions in our understanding of the physical world. While Einstein was busy dismantling the classical, Newtonian concepts of absolute space and time, another equally profound revolution was taking place in the heart of Europe, a revolution that would reveal the strange, probabilistic, and deeply counterintuitive nature of reality at the smallest scales. This was the birth of quantum mechanics. The story begins in 1900 with the German physicist Max Planck, while trying to solve a puzzle related to the nature of the light emitted by hot objects, a problem known as the blackbody radiation problem. Planck was forced to make a radical and desperate assumption. He proposed that energy is not a continuous quantity, but is emitted and absorbed in discrete, tiny packets, which he called quanta. This was a revolutionary idea, one that went against all the principles of classical physics, and even Planck himself was deeply uneasy with it. But it was a young Albert Einstein who, in 1905, his miracle year, took Planck's idea and ran with it. He proposed that light itself is not a continuous wave, but is composed of these tiny, indivisible bundles of energy, which we now call photons. This was the birth of the wave-particle duality, the idea that light can behave both like a wave and like a particle, a concept that would become a central and enduring paradox of the quantum world. Building on this idea, the French physicist Louis de Broglie, in 1923, made an even bolder leap. He hypothesized that if waves like light can behave like particles, then perhaps particles like electrons should also behave like waves. This was a stunning and audacious proposal, and it was soon confirmed by experiment. The double-slit experiment, which had long been used to demonstrate the wave-like nature of light, was now performed with electrons, and to everyone's astonishment, it worked. A single electron, fired at a barrier with two slits, seemed to pass through both slits at once, creating an interference pattern on the detector screen. The unmistakable signature of a wave. This wave-particle duality is at the heart of the quantum mystery. An electron is not a little billiard ball, nor is it a simple wave. It is something else entirely. A quantum entity that exhibits both wave-like and particle-like properties, depending on how we choose to measure it. This led to the development of the wave function, a mathematical object that describes the probability of finding a particle at any given point in space. Before a measurement is made, the particle exists as a superposition of all possible states, a cloud of probability. The moment a measurement is made, this wave function collapses, and the particle is found at a single, definite location. This concept of the collapse of the wave function was deeply troubling to Einstein. It seemed to suggest that the act of observation itself was what brought reality into being, and it also seemed to imply a kind of instantaneous, spooky action at a distance that violated the principles of his own theory of relativity. He famously expressed his dissatisfaction with the probabilistic nature of the theory, declaring, "God does not play dice." But the experimental evidence was undeniable. The quantum world is a world of probabilities, of uncertainty, of superposition. The Danish physicist Niels Bohr, who became the philosophical leader of the quantum revolution, argued that we should simply accept this weirdness as a fundamental feature of nature. His Copenhagen interpretation of quantum mechanics, developed in collaboration with Werner Heisenberg, proposed that our classical concepts of wave and particle are just complementary and mutually exclusive ways of describing the quantum world. We can perform an experiment that reveals the particle nature of an electron, or we can perform an experiment that reveals its wave nature, but we can never do both at the same time. The question, what is an electron really, is, in this view, a meaningless one. It is only in the context of a specific experimental setup that the electron's properties become definite. This is the principle of complementarity, and it is deeply connected to Heisenberg's uncertainty principle, which places a fundamental limit on what we can know about the quantum world. The debate between Einstein, with his desire for a deeper deterministic and locally real theory, and Bohr, with his embrace of uncertainty, complementarity, and the central role of the observer, was one of the great intellectual duels of the 20th century. While Einstein's intuition led to some of the most powerful thought experiments in the history of physics, such as the EPR paradox, which highlighted the spooky nature of quantum entanglement, it was Bohr's interpretation that ultimately seemed to be borne out by experiment. The universe, at its deepest level, does not seem to care about our classical, common-sense intuitions. It is a world of strange and beautiful paradoxes, a world where a particle can be in many places at once, where the future can influence the past, and where the very act of looking at something seems to change what is there. It is a world that is far stranger and far more mysterious than any of our classical theories could have ever imagined. The quest to build a quantum theory of the fundamental forces of nature was one of the great triumphs of 20th century physics. It was a journey that took the strange and counterintuitive principles of quantum mechanics and applied them to the classical field theories of Maxwell and others, resulting in a new and powerful framework known as quantum field theory. But boy, this is the language in which our modern standard model of particle physics is written. In QFT, the fundamental reality is not particles, but fields. There is an electron field, a quark field, a photon field, and so on. And these fields permeate all of space-time. The particles we observe are just the quantized excitations, the ripples, the vibrations of these underlying fields, and the forces between these particles are not a spooky action at a distance, but are mediated by the exchange of other particles, the force-carrying or messenger particles. In the case of the electromagnetic force, this messenger particle is the photon. When two electrons repel each other, they are not directly pushing on each other. They are exchanging virtual photons, like two ice skaters throwing bowling balls at each other. The recoil from throwing and catching the bowling balls pushes the skaters apart. In the same way, the exchange of virtual photons mediates the electromagnetic force. This framework was first developed for the electromagnetic force in the 1940s in a theory known as quantum electrodynamics. It was a stunningly successful theory, making predictions that have been experimentally verified to an incredible degree of precision. It was later extended to the other two fundamental forces of the Standard Model, the weak nuclear force and the strong nuclear force. The weak force, which is responsible for certain types of radioactive decay, is mediated by heavy messenger particles called the W and Z bosons. The strong force, which binds quarks together inside protons and neutrons and holds the atomic nucleus together, is mediated by massless particles called gluons. All of these forces, and all of the matter particles they act upon, are described with breathtaking accuracy by the Standard Model. And at the heart of this model lies a deep and beautiful principle, the principle of gauge symmetry. A gauge symmetry is a kind of mathematical redundancy in our description of a physical system. It means that we can change or transform the underlying quantum fields in a certain way at every point in space-time, and the physical predictions of the theory will remain exactly the same. The universe, it seems, has a deep underlying symmetry. But here is the crucial insight, first developed by Hermann Weyl and later by Chen-Ning Yang and Robert Mills. If you demand that a theory has a particular gauge symmetry, then the existence of a corresponding force, mediated by a messenger particle, becomes a mathematical necessity. The force is required to keep the physics unchanged under the symmetry transformation. The electromagnetic force, for example, is a necessary consequence of a gauge symmetry known as U symmetry. The strong force is a consequence of SU symmetry, which is related to the color charge of quarks, and the weak force, along with electromagnetism, is a consequence of a combined SU-XU symmetry. This is a profound and powerful idea. It suggests that the forces of nature are not arbitrary, but are a necessary consequence of the deep, underlying mathematical symmetries of the universe. It is a vision of a cosmos that is not just a random collection of particles and forces, but is governed by a deep, elegant, and unifying mathematical logic. This vision, however, has one glaring omission: gravity. The great dream of 20th century physics was to find a similar quantum field theory description of gravity, to find the gauge symmetry that gives rise to the gravitational force, and to identify its messenger particle, the hypothetical graviton. But this quest has proven to be incredibly difficult. When physicists try to apply the standard techniques of quantum field theory to Einstein's theory of general relativity, the mathematics breaks down. The calculations are plagued by uncontrollable, infinite results, a sign that the theory is incomplete. The problem lies in the fundamentally different nature of gravity. In the standard model, the other forces are actors on a fixed, static stage of space-time. But in general relativity, gravity is the stage. It is the dynamic, curving geometry of space-time itself. To quantize gravity is to quantize space-time, and this is where the trouble begins. At the incredibly small sub-Planck length scales, the uncertainty principle of quantum mechanics implies that space-time itself should be a chaotic, roiling quantum foam of violent fluctuations. The smooth, geometric picture of general relativity breaks down completely. The two great pillars of modern physics, general relativity and quantum mechanics, which work so perfectly in their own domains, seem to be fundamentally, irreconcilably, at war with each other at the ultimate frontier of reality. The resolution of this deep and profound conflict is the central challenge of 21st century theoretical physics, and it is a challenge that has led to some of the most ambitious, most beautiful, and most speculative ideas in the history of science. Ideas like string theory, the dream of a unified theory, a single framework that could encompass all the forces and particles of nature, including gravity, has been the driving force of fundamental physics for the better part of a century. And for the last few decades, the most promising and most controversial candidate for such a theory has been string theory. It is a theory of breathtaking ambition and profound mathematical elegance, and it proposes a radical and fundamental shift in our understanding of reality. At its core, string theory's proposal is simple. The fundamental constituents of the universe are not point-like, zero-dimensional particles, but tiny, one-dimensional, vibrating strings of energy. These are not strings in the ordinary sense. They are unimaginably small, with a characteristic length of around the Planck length, 10 to the power of minus 33 centimeters. If an atom were magnified to the size of the observable universe, one of these strings would be about the size of a tree. In this picture, the rich and diverse zoo of elementary particles that we observe in nature The quarks, the leptons, the photons, the gluons are not different things. They are all made of the same fundamental stuff, a single vibrating string. The differences between the particles arise from the different ways that these strings can vibrate. Just as the string of a violin can vibrate in different patterns to produce different musical notes, a C, a G, and E-flat, so too can the fundamental strings of the universe vibrate in different modes to produce the different particles we see. An electron is a string vibrating in one pattern. A photon is a string vibrating in another. A quark is a string vibrating in yet another. The properties of these particles, their mass, their electric charge, their spin, their other force charges, are all determined by the precise, resonant pattern of the string's vibration. This is a unification of unprecedented power and beauty. All the matter and all the forces of nature are brought under a single, unifying umbrella. The universe, in this view, is a cosmic symphony, a rich and complex harmony played out on the vibrating strings of reality. The laws of physics are the rules of harmony, the principles that govern which notes can be played. And the universe we inhabit is the particular, beautiful, and complex piece of music that has been composed from these fundamental notes. One of the most remarkable and compelling features of string theory is that gravity is not an optional extra. It is a necessary and unavoidable consequence of the theory. Among the infinite number of possible vibrational patterns of the string, there is one that has the precise properties of the hypothetical graviton, the quantum particle that is thought to mediate the force of gravity. String theory does not just accommodate gravity, it demands it. This was a stunning and unexpected discovery, and it is one of the primary reasons why so many physicists have been drawn to the theory. But this beautiful unifying picture comes with a set of extraordinary and challenging consequences. The first is that, for the theory to be mathematically consistent, it requires the existence of extra hidden dimensions of space. The world we perceive has 3 spatial dimensions and 1 of time. But string theory predicts that the universe actually has 9 or 10 spatial dimensions, for a total of 10 or 11 space-time dimensions. The extra 6 or 7 dimensions are not something we can see or experience directly. They are thought to be compactified, curled up into a tiny, complex, geometrical shape at every point in our familiar 3-dimensional space. The geometry of these extra dimensions is not just a mathematical curiosity. It is the key to the theory's predictive power. The precise shape and size of this Calabi-Yau manifold determines the possible vibrational patterns of the strings, and therefore, it determines the entire spectrum of particles and forces that we observe in our universe. The laws of physics are a reflection of the geometry of these hidden dimensions. The second major challenge is the landscape problem, string theory. It turns out, does not predict a unique geometry for the extra dimensions. It allows for a vast, and possibly infinite, number of different stable Calabi-Yau manifolds, each corresponding to a different vacuum state, a different set of physical laws. This has led to the idea of the string theory landscape, a multiverse of at least 10 to the power of 500 different possible universes. This is a source of great debate and controversy within the physics community. For some, it is a fatal flaw, a sign that the theory is not truly predictive. For others, it is the theory's greatest strength, providing a natural home for the anthropic principle and an explanation for the apparent fine-tuning of our own universe. And finally, there is the challenge of experimental verification. The energies required to directly probe the Planck scale and to see the string-like nature of particles are many orders of magnitude beyond the reach of our current or foreseeable technology. This has led to the criticism that string theory is not a true scientific theory, but a form of mathematical philosophy. But the proponents of string theory are not deterred. They argue that the theory's internal consistency, its mathematical beauty, and its ability to unify gravity and quantum mechanics are strong indications that it is on the right track, and they are actively searching for indirect, low-energy consequences of the theory that might be testable, such as the existence of supersymmetric particles, the precise pattern of neutrino masses, or subtle signatures in the cosmic microwave background. String theory is still very much a work in progress, a beautiful and ambitious mathematical framework that is still searching for its definitive physical form, but it represents our boldest and most profound attempt yet to read the mind of God, to find the single, elegant equation that can describe the entire magnificent symphony of the cosmos. The fundamental conflict between the two great pillars of modern physics, general relativity and quantum mechanics, becomes most acute at the very smallest of scales. General relativity, with its vision of a smooth, continuous, and dynamic space-time, works beautifully for describing the large-scale structure of the universe. But when we try to zoom in, to look at the fabric of space-time at the Planck length, the uncertainty principle of quantum mechanics tells us that this smooth picture must break down. At these incredibly small distances, the zero-point energy of the gravitational field itself would lead to violent, chaotic quantum fluctuations in the very geometry of space and time. This is the quantum foam, a roiling, turbulent sea of virtual black holes and wormholes, where the concepts of distance and duration lose their meaning. The combination of the equations of general relativity and quantum mechanics in this regime leads to nonsensical infinite results, a clear sign that our theories are incomplete. String theory offers a radical and elegant solution to this problem. By replacing the zero-dimensional, point-like particles of our conventional theories with one-dimensional, extended strings, the theory effectively smears out the interactions between them. In a point-particle theory, an interaction happens at a single, infinitely small point in space-time. This is what leads to the problematic infinities. But in string theory, an interaction is no longer a single point. When two strings collide, they merge and split over a small, but finite, region of space-time. The interaction is smeared out, and this smearing has a profound effect. It softens the violent, short-distance quantum fluctuations of space-time. It tames the quantum foam. And it eliminates the problematic infinities that have plagued all previous attempts to build a quantum theory of gravity. The strings are too large to be sensitive to the sub-Planck scale chaos. It is like trying to feel the microscopic bumps on a polished granite surface with your finger. Your finger is too large. It averages over the bumps, and the surface feels smooth. In the same way, the strings average over the quantum foam, and they experience a smooth, well-behaved space-time. This is a profound and beautiful insight. It suggests that the very existence of a minimum size for the fundamental constituents of nature, the fact that they are strings and not points, is what saves the universe from the mathematical pathologies of an infinitely chaotic quantum space-time. String theory, in this sense, sets a fundamental limit to the resolution with which we can probe the universe. There is a minimum length, on the order of the Planck length, below which the very concept of distance becomes meaningless. This is not a limitation of our technology. It is a fundamental feature of reality as described by the theory. This idea of a minimum length has been explored in other approaches to quantum gravity as well, and it is a recurring theme in the search for a unified theory. It suggests that the continuous, infinitely divisible space-time of classical physics is an illusion, an approximation that breaks down at the ultimate frontier of reality. But the beauty of string theory is that this minimum length is not an ad hoc assumption. It is a direct and necessary consequence of the theory's internal mathematical consistency. And this resolution of the conflict between general relativity and quantum mechanics is not the only triumph of the theory. It also, as we have seen, provides a natural home for a zoo of other higher dimensional objects known as brains. In the mid-1990s, in what has been called the second superstring revolution, physicists discovered that the 5 seemingly different, consistent string theories that had been developed were actually just different aspects of a single, underlying 11-dimensional theory, known as M-theory. In this deeper, more mysterious theory, strings are not the only fundamental objects. There are also 2-dimensional membranes, 3-dimensional volumes, and so on, up to 9-dimensional 9-branes. Our entire observable universe could be a 3-brane, a vast 3-dimensional membrane floating in a higher dimensional, 11-dimensional bulk space. This brain world scenario opens up a host of new and exciting possibilities. It could explain the weakness of gravity. It could provide a home for dark matter. And it could lead to new cyclical models of the cosmos. The journey into the heart of string theory is a journey into a world of incredible mathematical beauty, of hidden dimensions, of vibrating strings and higher dimensional brains. It is a world that is far removed from our everyday experience, a world that is still shrouded in deep mystery and profound, unanswered questions. But it is a world that may hold the key to the ultimate unification of all the laws of nature, the key to a final, complete, and beautiful understanding of the deep, string-like music of the cosmos. The existence of extra hidden dimensions of space is one of the most striking and counterintuitive predictions of string theory, and yet it is a necessary one. The mathematics of the theory simply does not work in our familiar 3 spatial dimensions. The calculations are plagued by nonsensical, negative probabilities and other mathematical inconsistencies. It is only when the strings are allowed to vibrate in 9 spatial dimensions that these inconsistencies magically cancel out, and a consistent, well-behaved quantum theory emerges. This is a powerful and deeply mysterious constraint. It is as if the universe itself is telling us, through the language of mathematics, that the reality we perceive is not the whole of reality. But if these extra dimensions exist, where are they? And why don't we see them? The answer, first proposed by Theodore Kaluza and Oscar Klein in the 1920s in a different context, is that the extra dimensions are compactified, or curled up, into a tiny subatomic size. Imagine a long, thin straw. From a great distance, it appears to be a one-dimensional line. But as you get closer, you realize that at every point along the line, there is a second circular dimension that you can travel around. The extra dimensions of string theory are thought to be like this circular dimension of the straw, but far, far smaller, curled up on a scale of around the Planck length. They are so small that they are completely inaccessible to our senses and even to our most powerful particle accelerators. We are like giants, lumbering through a 3-dimensional world, completely unaware of the tiny, intricate, 6-dimensional geometry that exists at every single point in the space around us. But these hidden dimensions are not just a mathematical curiosity. They are the key to the theory's predictive power. The geometry of these extra dimensions, the precise way in which they are curled up and twisted, determines the allowed vibrational patterns of the strings. And since the vibrational patterns of the strings determine the properties of the particles we observe, it means that the entire physics of our universe, the masses of the quarks and leptons, the strengths of the fundamental forces, the number of particle families, is a direct consequence of the geometry of these hidden 6-dimensional spaces. The laws of nature are a reflection of the shape of the universe's extra dimensions. This is a stunning and profound idea. It suggests that the answers to some of the deepest questions in particle physics. Why are there 3 families of particles? Why do they have the masses they do? Are not to be found in the particles themselves, but in the geometry of a higher dimensional space. The search for the fundamental laws of physics becomes a search for the correct Calabi-Yau manifold, the specific type of six-dimensional, complex geometrical shape that is required by the consistency of string theory. The problem is that there are a vast number of possible Calabi-Yau manifolds, perhaps as many as 10 to the power of 500, each corresponding to a different, consistent set of physical laws. This is the landscape problem, and it is one of the greatest challenges facing string theory. If the theory allows for such a vast number of possible universes, how can it ever make a unique, falsifiable prediction for our own? The answer, for some, lies in the anthropic principle and the multiverse. But for others, it is a sign that our understanding of the theory is still incomplete, that there must be some as yet undiscovered principle that selects a unique Calabi-Yau manifold, a unique set of physical laws for our universe. The question of why our universe has 3 large, extended spatial dimensions and 6 tiny, curled-up ones is another deep and unsolved mystery. Some cosmological models have proposed that in the very early universe, all the dimensions may have started out small and curled up, and that some dynamical process, perhaps related to cosmic inflation, caused 3 of them to rapidly expand to their current vast size, while the others remained trapped at the Planck scale. These are all ideas that are on the cutting edge of theoretical physics, ideas that are pushing the boundaries of our mathematics and our imagination. But they all point to the same remarkable conclusion that the world we see, the familiar world of 3 spatial dimensions, may just be a slice, a projection, of a much richer, much deeper, and much more complex higher dimensional reality. And that the secrets of our own familiar world may be hidden in the beautiful, intricate, and invisible geometry of the universe's other, hidden dimensions. The quest for a final unified theory of everything, a quest epitomized by string theory, is one of the grandest and most ambitious endeavors in the history of human thought. And yet, it is an endeavor that is not without its critics. The very idea of a theory of everything can seem arrogant, a hubristic attempt to put the infinite, mysterious universe into a neat, tidy, and finite human-made box. And string theory, in particular, has faced a growing chorus of criticism in recent years, not just from philosophers, but from within the physics community itself. The criticisms are varied and powerful. Some argue that the theory's reliance on mathematical beauty as a guide to truth is a dangerous and potentially misleading path. The history of science is littered with beautiful, elegant theories that turned out to be wrong. Kepler's beautiful, Platonic model of the solar system, with the planetary orbits inscribed within a nested series of regular polyhedra, was a mathematical masterpiece. But it had nothing to do with the way the solar system actually works. The physicist Paul Dirac famously said that it is more important to have beauty in one's equations than to have them fit experiment. But the physicist Sabine Hossenfelder, in her book Lost in Math, has argued that this modern obsession with mathematical beauty has led a generation of theoretical physicists down a rabbit hole of elegant, but ultimately untestable and physically irrelevant ideas. The primary and most potent criticism of string theory is precisely this, its lack of testability. The theory's fundamental predictions, such as the existence of strings, extra dimensions, and a whole host of new supersymmetric particles, are all at the Planck scale, an energy regime that is a quadrillion times higher than anything we can reach with our current particle accelerators. Building an accelerator powerful enough to directly probe this scale would require a machine the size of our galaxy. In the absence of direct experimental evidence, how can we ever know if the theory is right? How can it be distinguished from a beautiful but purely mathematical fantasy. The theory's defenders argue that this criticism is unfair. All scientific theories, they say, have a domain of applicability, and it is not a flaw in a theory if its direct predictions lie beyond our current technological reach, and they point to the possibility of indirect evidence. The existence of supersymmetry, for example, is a generic prediction of most string theory models, and the discovery of supersymmetric particles at the Large Hadron Collider would be a major circumstantial piece of evidence in the theory's favor. The fact that no such particles have yet been found has been a major disappointment for the field. Another avenue for indirect evidence could be cosmology. The precise details of cosmic inflation, the statistical properties of the cosmic microwave background, the nature of dark matter and dark energy, all of these could hold subtle clues. Faint fingerprints of an underlying stringy reality, the discovery of a fundamental particle that makes up dark matter, for example, and the measurement of its properties could provide a crucial test of the predictions of different string theory models. The debate over the scientific status of string theory is a healthy and necessary one. It forces the theory's proponents to be more rigorous, to search for more testable predictions, and to confront the theory's deep conceptual challenges, like the landscape problem. And it forces the theory's critics to acknowledge its immense theoretical power, its mathematical beauty, and its remarkable ability to unify the seemingly disparate worlds of gravity and quantum mechanics. The quest for a theory of everything is a journey into the unknown, a journey that is fraught with uncertainty, with controversy, and with the very real possibility of failure. But it is a journey that is driven by one of the deepest and most noble of all human impulses, the desire to understand, to find a sense of order and meaning in a vast and often chaotic universe, to read the mind of God. Whether string theory is the final chapter in this long and beautiful story, or just another fascinating and ultimately incorrect chapter remains to be seen. But the quest itself, the bold and courageous attempt to grasp the ultimate nature of reality, is a testament to the incredible power and the incredible beauty of the human mind. The revolution in our understanding of the cosmos that was ignited by Einstein's theories of relativity is a story of profound and counterintuitive insights into the nature of space, of time, and of gravity. And yet, for all its power and beauty, general relativity is an incomplete theory. It is a classical theory, a theory that does not incorporate the strange and wonderful principles of the quantum world. This incompleteness becomes a critical failure at the very heart of the theory's most dramatic predictions, the singularity at the beginning of the Big Bang and the singularity at the center of a black hole. These are points where the theory predicts that the density of matter and the curvature of space-time become infinite, a clear sign that the theory itself is broken down and is no longer applicable. To understand these ultimate frontiers of reality, we need a quantum theory of gravity. And one of the most promising and well-developed approaches to this profound challenge is loop quantum gravity. Unlike string theory, which starts with particles and forces and finds that gravity is a necessary consequence, LQG starts with space-time itself, with the very fabric of Einstein's general relativity, and attempts to quantize it directly, using the principles of quantum mechanics. The result is a vision of space-time that is as radical and as beautiful as that of string theory, but which arises from a completely different set of principles. In LQG, space is not a smooth, continuous background. It is a discrete, granular structure, a quantum fabric woven from fundamental, indivisible atoms of space. These atoms are not in space, they are space. Each of these quantum atoms has a volume on the order of the Planck length cubed, the smallest possible volume that can exist. And these atoms are not just scattered randomly, they are connected to each other in a complex, evolving network, a spin network. The geometry of space, the very concepts of area and volume, are determined by the combinatorial properties of this network. And the evolution of this spin network in time creates a spin foam, a quantum, four-dimensional space-time. This is a profound and radical idea. It suggests that the smooth, continuous space-time of our macroscopic experience is an illusion, an emergent property of a much deeper, discrete, and quantum reality. In the same way that the smooth, continuous flow of water is an emergent property of the discrete, jiggling motion of a vast number of H2O molecules. This quantization of space-time has a powerful and immediate consequence. It eliminates the singularities of general relativity. In LQG, there can be no such thing as an infinitely dense point. The granular nature of space itself provides a fundamental minimum size, a quantum bounce that prevents the catastrophic collapse to a singularity. When this idea is applied to the Big Bang, the initial singularity is replaced by a big bounce. In this scenario, our expanding universe may have been preceded by a previous contracting universe, as this previous universe collapsed under its own gravity. It did not reach a singularity. Instead, when it reached the Planck density, the repulsive quantum gravitational effects of the space-time foam became dominant, causing the collapse to halt and bounce into the expanding phase of our own universe. The Big Bang was not a beginning, but a transition. Similarly, at the center of a black hole, the singularity is replaced by a Planck star, an incredibly dense but finite object where the collapsing matter is held up by the quantum pressure of space-time itself. This Planck star may eventually, after the black hole has evaporated through Hawking radiation, bounce and release the information that was trapped inside, providing a potential solution to the black hole information paradox. LQG is a beautiful and conceptually powerful theory, and it has had a number of significant successes, such as providing a first principles calculation of the entropy of a black hole. But it is also a theory that is still very much a work in progress. It has struggled to show how the smooth, classical space-time of general relativity can emerge from its underlying discrete quantum structure. And it does not, as yet, provide a natural unification of gravity with the other forces and particles of the Standard Model. The debate between string theory and loop quantum gravity is one of the central intellectual dramas of modern theoretical physics. They are two, very different and seemingly incompatible, paths to the same ultimate goal. Whether one of them will prove to be correct, or whether the true theory of quantum gravity will be something else entirely, a synthesis of ideas from both remains to be seen. But the very existence of a theory like LQG is a powerful testament to the fact that our understanding of space and time is still in its infancy, and that the true nature of the cosmic fabric may be far stranger, more discrete, and more beautifully quantum than we ever imagined. The legacy of Stephen Hawking's work on black holes is a profound and beautiful illustration of the deep and fruitful interplay between general relativity, quantum mechanics, and thermodynamics. It is a story that begins with a simple observation about the area of a black hole's event horizon and ends with a deep and troubling paradox about the very nature of information. In the early 1970s, Hawking proved a powerful theorem in classical general relativity, the area theorem, which states that the surface area of a black hole's event horizon can never decrease over time. It can only stay the same, or increase, as the black hole swallows more matter. This had a striking and familiar ring to it. There is another quantity in physics that is famous for never decreasing entropy, the measure of a system's disorder, as described by the second law of thermodynamics. This led the Israeli-American physicist Jacob Bekenstein to make a bold and brilliant proposal that the area of a black hole's event horizon is, in fact, a measure of its entropy. This was a radical idea. In classical thermodynamics, entropy is related to temperature, and an object with entropy must have a temperature, and an object with a temperature must radiate energy. But in classical general relativity, black holes are perfectly black. Nothing can escape them. They should have a temperature of absolute zero. At first, Hawking himself was deeply skeptical of Bekenstein's idea. He set out to prove it wrong by applying the principles of quantum field theory to the curved space-time around a black hole's event horizon. And what he found was one of the most stunning and unexpected discoveries in the history of physics. He found that Bekenstein was right. Black holes are not completely black. They do have a temperature, and they do radiate. Due to the quantum fluctuations of the vacuum near the event horizon, a process that is now known as Hawking radiation, black holes slowly, almost imperceptibly, emit a faint thermal radiation of particles. This discovery beautifully unified the three great pillars of modern physics. The formula for the temperature of a black hole contains Planck's constant, Newton's gravitational constant, and Boltzmann's constant. It is a single, elegant equation that connects all three domains of reality. And it confirmed Bekenstein's intuition: the entropy of a black hole is indeed proportional to the area of its event horizon. This led to the formulation of the generalized second law of thermodynamics, which states that the total entropy of the universe, the sum of the entropy of the ordinary matter and radiation outside the black hole, and the entropy of the black hole itself, can never decrease. If you throw a hot cup of tea into a black hole, the entropy of the outside world decreases, but the entropy of the black hole, as measured by its area, increases by an even greater amount, ensuring that the total entropy of the universe always goes up. The laws of black hole thermodynamics are a beautiful and profound extension of the laws of classical thermodynamics to the realm of gravity and quantum mechanics. But Hawking's discovery also created a deep and troubling puzzle: the black hole information paradox. Quantum mechanics is built on the principle of unitarity, the idea that information is never truly lost. The wave function of the universe contains all the information about its past, present, and future, and it evolves in a perfectly deterministic way. But black holes seem to violate this principle. If you throw an encyclopedia into a black hole, all the complex information contained in its pages seems to be lost forever behind the event horizon. And when the black hole eventually evaporates through Hawking radiation, the radiation it emits is purely thermal, random, and seems to contain no memory of the specific information that fell in. So, where did the information go? Is it truly destroyed, in violation of the most fundamental principle of quantum mechanics, or does it somehow escape, subtly encoded in the quantum correlations of the outgoing Hawking radiation? This paradox has been at the center of theoretical physics for decades, and it has led to some of our deepest insights into the nature of quantum gravity. Loop quantum gravity, with its discrete quantum geometry, offers a potential solution. In LQG, the singularity at the center of a black hole is replaced by a Planck star, and the information that falls into the black hole may be preserved in this quantum remnant, to be released at the very end of the black hole's evaporation. String theory, with its holographic principle, offers another. It suggests that the information is never truly lost inside the black hole, but is encoded on the two-dimensional surface of its event horizon, like a cosmic hologram, and is then slowly and subtly imprinted onto the outgoing Hawking radiation. The information paradox is a sign that we are at the very edge of our understanding, at the point where our two great theories of reality, general relativity and quantum mechanics, collide in a spectacular and beautiful contradiction. The resolution of this paradox will require a new, deeper, and more unified theory of nature, a theory of quantum gravity that can finally tell us the ultimate fate of the information that dares to venture beyond the point of no return. The fundamental nature of our universe, as revealed by our most successful physical theories, is that of a world built from quantum fields. This is the central insight of the standard model of particle physics and the broader framework of quantum field theory. The universe is not a collection of solid, inert, billiard ball-like particles. It is a vast, interconnected, and dynamic web of invisible, all-pervading fields. There is an electron field, a photon field, a Higgs field, and so on, one for each of the fundamental constituents of nature. The particles that we observe in our experiments are just the localized, quantized vibrations, the quanta of these underlying fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. And the forces between these particles are mediated by the exchange of other ripples, other quanta, the force-carrying bosons. This is a profound and radical shift in our worldview, a shift from a world of things to a world of processes, from a world of substance to a world of form. But this beautiful and powerful picture has a deep and unresolved tension at its heart, a tension that arises when we try to incorporate the force of gravity into this quantum field theoretic framework. In the standard model, the other three forces are described as quantum fields that exist on a fixed, pre-existing stage of space-time. But in Einstein's theory of general relativity, gravity is not a force that exists on the stage. It is the stage. Gravity is the dynamic, curving geometry of space-time itself. So, to build a quantum theory of gravity, we must quantize space-time. This is the central challenge, and it is a challenge that has led to two very different and seemingly incompatible approaches. The first approach, the one favored by most of the particle physics community, is to treat gravity like the other forces. In this view, there should be a graviton field, a quantum field of gravity that exists on a fixed background space-time, and there should be a corresponding quantum particle, the graviton, a massless spin-tube boson that mediates the gravitational force. When two massive objects attract each other, they are exchanging virtual gravitons. This is a natural and appealing picture, and it is the picture that underlies string theory, where the graviton emerges as one of the vibrational modes of the fundamental string. The problem with this approach is that when you try to apply the standard techniques of quantum field theory to the graviton field, the calculations are plagued by uncontrollable, non-renormalizable infinities. The theory breaks down at high energies. The second approach, the one taken by loop quantum gravity, is more radical. It takes Einstein's central insight that gravity is geometry seriously, and it attempts to quantize geometry itself. In this background-independent approach, there is no pre-existing stage of space-time. Space-time itself is an emergent quantum phenomenon, a dynamic network of interconnected atoms of space and time. In this picture, there is no need for a graviton particle that travels through space to mediate the force of gravity. Gravity is simply the large-scale, collective behavior of the quantum geometry of space-time itself. So, where does this leave the graviton? Is it a fundamental particle or a convenient fiction? The answer may be that it is both and neither. The wave-particle duality of quantum mechanics tells us that the distinction between a wave and a particle is not absolute. A gravitational wave, a ripple in the fabric of space-time, can also be thought of as a coherent stream of a vast number of gravitons, in the same way that a beam of light can be thought of as a stream of photons. The detection of gravitational waves in 2015 by the LIGO experiment was a stunning confirmation of one of the key predictions of general relativity. And while we cannot detect an individual graviton, it is reasonable to infer that these waves are, in fact, made of a vast number of these quantum particles of gravity. In the same way, the vibrational modes of a crystal lattice, which are waves, can also be described as quantum particles, called phonons. Phonons are not fundamental particles, but are quasi-particles, emergent, collective excitations of the underlying atomic lattice. Perhaps the graviton is like a phonon. It is not a fundamental particle that exists on a fixed background, but is an emergent, collective excitation of the underlying, discrete quantum geometry of space-time itself. This would be a beautiful synthesis of the two, seemingly opposing, views. Gravity is geometry, as Einstein taught us. But that geometry is, at its core, a quantum system, and its ripples, its vibrations, its quanta, are what we call gravitons. The search for a quantum theory of gravity is a search for the deep, underlying language that can speak of both the geometric elegance of Einstein's cosmos and the probabilistic quantum nature of the subatomic world. And in this new language, the old classical distinctions between space, time, matter, and force may all dissolve into a new, more profound, and more beautiful unified reality. The standard model of inflationary Big Bang cosmology, while stunningly successful, is a story that begins in the midst of the action. It describes the evolution of the universe from a hot, dense, and rapidly expanding initial state. But it is silent on the question of the ultimate origin. It is a story with a first chapter, but no preface. The initial singularity, the point of infinite density and temperature where the story begins, is not a physical reality, but a confession of ignorance, a point where our current laws of physics break down. To understand what might have come before the Big Bang, or what might have caused it, we must venture beyond the realm of classical general relativity and into the strange and speculative world of quantum cosmology. And it is here, in the application of quantum principles to the universe as a whole, that we find a number of fascinating and potentially revolutionary new ideas. The central challenge is to build a theory of quantum gravity, a theory that can describe the universe in its earliest, most extreme moments, when both quantum effects and strong gravity were important. Loop quantum gravity, with its vision of a discrete, granular space-time, offers one of the most well-developed approaches to this challenge. And when the principles of LQG are applied to the early universe, a remarkable and beautiful picture emerges. The Big Bang singularity is gone. It is replaced by a big bounce. In this scenario, our expanding universe was preceded by a previous contracting universe. As this parent universe collapsed under its own gravity, it did not fall into an infinitely dense singularity. Instead, when it reached the incredibly high but finite Planck density, the discrete quantum nature of space-time itself kicked in. The atoms of space resisted being squeezed any further, creating a powerful, repulsive quantum gravitational force that halted the collapse and caused the universe to bounce into the expanding phase of our own cosmic eon. The Big Bang was not a beginning from nothing, but a transition, a moment of cosmic rebirth. This is a profoundly elegant and satisfying idea. It eliminates the problematic singularity, and it opens up the possibility of a universe that is eternal and cyclical. The history of the cosmos is no longer a linear story with a mysterious singular beginning, but an endless rhythmic dance of expansion and contraction, of death and rebirth. The development of this loop quantum cosmology has been a long and painstaking process, a journey of refining the mathematical models and the computational simulations to get a physically sensible picture. Early versions of the theory had their own problems, but through years of dedicated work, a consistent and robust model has emerged. In this model, the effects of quantum geometry appear as a correction to the classical equations of Einstein's general relativity. This correction term becomes significant only at extremely high densities, close to the Planck scale. At lower densities, the quantum effects are negligible, and the theory smoothly reproduces the predictions of classical general relativity, a crucial requirement for any new theory. The LQC model of the Big Bounce is not just a beautiful qualitative idea. It makes specific, testable predictions. It predicts a slightly different pattern of fluctuations in the cosmic microwave background than the standard inflationary model, a difference that could, in principle, be detected by future high-precision CMB experiments. It also offers a natural mechanism for generating a period of inflation after the bounce, potentially solving the horizon and flatness problems without the need for a separate, ad hoc inflaton field. The journey to understand our ultimate origins is a journey to the very heart of the mystery of time, of space, and of existence itself. And while we are still far from a final, definitive answer, the vision of a bouncing, cyclical, and eternal universe offered by loop quantum cosmology is one of the most compelling and beautiful stories that modern science has to tell. It is a story that replaces a singular, inexplicable miracle with a natural, dynamic, and potentially endless cosmic process. A story that suggests that our universe is not a one-off event, but a single, precious breath in the infinite and eternal respiration of the cosmos. The formation of our own solar system, a seemingly local and familiar event, is a story whose roots stretch back to the very beginning of the universe and are governed by the same deep, quantum mechanical principles that shape the cosmos at its largest and smallest scales. The story begins, as all cosmic stories do, in the aftermath of the Big Bang. The initial, hot, dense soup of particles cooled and expanded, and the tiny quantum fluctuations of the early universe were stretched to astronomical scales, seeding the first, large-scale structures of the cosmic web. Within the dense filaments of this web, vast clouds of hydrogen and helium gas began to collapse under their own gravity, fragmenting into the first galaxies and the first generations of stars. It was in one such cloud, in a quiet, suburban spiral arm of the Milky Way galaxy, about 4.6 billion years ago, that our own solar system began to take shape. The process of star and planet formation is a delicate and complex dance between the inward pull of gravity and the outward push of pressure and radiation, a dance that is, at its core, a quantum mechanical one. As a dense clump within a molecular cloud begins to collapse, it forms a spinning, central protostar, surrounded by a flattened, rotating protoplanetary disk of gas and dust. It is from this disk that the planets are born, and the very process that powers the young sun at the center of this disk is a quantum mechanical miracle nuclear fusion. In the incredibly hot and dense core of the protostar, the conditions are not quite extreme enough for hydrogen nuclei to overcome their mutual electrostatic repulsion and fuse together, according to the laws of classical physics. It is only through the strange probabilistic magic of quantum tunneling that these nuclei can get close enough for the strong nuclear force to take over, igniting the stellar furnace and beginning the long, stable, hydrogen-burning phase of the star's life. Without quantum tunneling, our sun would never have ignited, and our solar system would be a cold, dark, and lifeless place within the protoplanetary disk. The process of planet formation is also governed by quantum principles. At the microscopic level, tiny submicron dust grains, coated with a mantle of water ice and other frozen volatiles, begin to stick together. The forces that govern this initial clumping, the van der Waals forces, the electrostatic interactions, are all fundamentally quantum electrodynamic in nature, As these dust grains grow into larger pebbles, and the pebbles into kilometer-sized planetesimals, the process becomes dominated by gravity. But the very existence of the solid matter from which these planetesimals are built is a quantum story. The heavy elements that make up the rocky terrestrial planets, like our Earth, the carbon, the oxygen, the silicon, the iron, were not created in the Big Bang. They were forged in the nuclear furnaces of previous generations of massive stars. These stars, at the end of their lives, exploded as supernovae, scattering these newly created elements across the galaxy, enriching the interstellar medium and providing the raw chemical materials for the next generation of stars and planets. The very process of nucleosynthesis, the creation of these heavy elements, is a quantum mechanical one, governed by the laws of the strong and weak nuclear forces. We are, in the most literal sense, the children of the stars, our bodies made of the recycled ash of long-dead suns. Even the final architecture of our solar system, the stable, ordered arrangement of the planets in their orbits, is a product of its quantum origins, the distribution of mass and energy in the primordial protoplanetary disk. A distribution that was itself a relic of the initial quantum fluctuations of the universe, determined the locations where planets could form and the amount of material that was available for them to accrete. The stability of our solar system, the delicate gravitational dance that has allowed for the long, uninterrupted period of climatic stability that was necessary for the evolution of complex life on Earth, is a fortunate consequence of this initial quantum roll of the dice. The story of our solar system's birth is a beautiful and powerful illustration of the deep, seamless connection between the microscopic and the macroscopic, between the quantum and the cosmic. It is a story that shows us that our own familiar world is not a separate, classical reality, but is a direct and intricate expression of the same, deep, quantum mechanical laws that govern the entire, vast and mysterious universe. The classical picture of a black hole, as a simple, featureless object described only by its mass, charge, and spin, has been profoundly enriched and complicated by the insights of quantum mechanics. The discovery of Hawking radiation revealed that black holes are not the eternal, static prisons they were once thought to be, but are dynamic, thermodynamic objects that have a temperature, an entropy, and a finite lifespan. But the quantum world has more surprises in store. The familiar Schwarzschild black hole, which is non-rotating and uncharged, is the simplest possible solution to Einstein's equations. But in the real universe, most black holes are likely to be spinning, a consequence of the angular momentum of the star that collapsed to form them. A spinning, or Kerr. Black hole is a far more complex and bizarre object. Its rotation drags the very fabric of space-time around with it, a phenomenon known as frame dragging. Near the event horizon, this effect is so strong that it creates a region called the ergosphere, a place where nothing can stand still. Any object in the ergosphere is forced to co-rotate with the black hole. This frame dragging has profound quantum mechanical consequences. The Penrose process, a theoretical mechanism proposed by Roger Penrose, suggests that it is possible to extract energy from a spinning black hole. A particle entering the ergosphere can split into two, with one particle falling into the black hole and the other escaping with more energy than the original particle had. The extra energy is effectively stolen from the black hole's rotational energy. Quantum mechanics adds a new twist to this. The constant creation of virtual particle pairs in the vacuum near the ergosphere can lead to a quantum version of the Penrose process, a phenomenon known as superradiance, which can amplify certain types of waves and extract energy from the black hole, causing it to spin down over time. Black holes can also have electric charge, creating a Reissner-Nordstrom black hole. The combination of gravity and electromagnetism around such an object creates a complex and fascinating environment. The presence of the electric field can affect the process of Hawking radiation, preferentially creating charged particle pairs from the vacuum. And in some extreme of theoretical cases, a charged and spinning Kerr-Newman black hole can have a naked singularity, a singularity that is not hidden behind an event horizon, a possibility that most physicists find deeply troubling, as it would represent a breakdown of causality, a place where the future is not determined by the past. The idea of extra dimensions, as predicted by string theory, adds another layer of exotic possibility. In a higher dimensional universe, black holes may not be spherical. They could be black strings, extending like a line in the extra dimensions, or black brains, two-dimensional surfaces. These higher dimensional black holes would have different thermodynamic properties and would evaporate through Hawking radiation in different ways. The search for these effects, either through gravitational wave observations of black hole mergers or through experiments at the Large Hadron Collider, is one of the most exciting frontiers in the search for extra dimensions. The study of black holes has also inspired the development of analog models in the laboratory. By using systems like flowing fluids, Bose-Einstein condensates, or even special optical materials, physicists can create dumb holes or optical black holes, systems that have an event horizon for sound waves or light waves. These analog models have allowed for the experimental observation of effects that are similar to Hawking radiation, providing a powerful, if indirect, confirmation of one of Hawking's most profound and counterintuitive predictions. The quantum world of black holes is a realm of incredible richness, complexity, and mystery. It is the ultimate laboratory for testing the interplay of our two most fundamental theories of nature, a place where gravity, quantum mechanics, thermodynamics, and information theory all come together in a beautiful and challenging synthesis. And it is a place that continues to yield deep and surprising insights into the fundamental nature of space, of time, and of reality itself. The black hole information paradox, the profound and troubling conflict between the predictions of general relativity and quantum mechanics, has been one of the central and most fruitful battlegrounds in theoretical physics for the last 50 years. The paradox, in its essence, is this: general relativity says that anything that falls into a black hole is lost forever, its information hidden behind the one-way membrane of the event horizon. Quantum mechanics, on the other hand, insists that information can never be truly destroyed, that the total amount of information in a closed system must be conserved. When a black hole evaporates through Hawking radiation, this conflict comes to a head. Does the information that fell into the black hole escape with the radiation, or is it destroyed forever? In violation of the most fundamental principle of quantum mechanics, the resolution of this paradox is thought to be a key stepping stone towards a full theory of quantum gravity. One of the most promising and powerful ideas to have emerged from this quest is the holographic principle, a concept first proposed by Gerard 't Hooft and later developed by Leonard Susskind. The principle is based on a surprising observation about the entropy of a black hole. The entropy of a normal thermodynamic system is proportional to its volume, but the entropy of a black hole, as shown by Bekenstein and Hawking, is proportional to the area of its event horizon. This suggests that all the information about the three-dimensional interior of the black hole is somehow encoded on its two-dimensional boundary. The event horizon, much like a three-dimensional image, can be encoded in a two-dimensional hologram. The holographic principle generalizes this idea, proposing that the entire universe may be a hologram. It suggests that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space, a theory with one fewer spatial dimension. This is a staggering and deeply counterintuitive idea. It suggests that the three-dimensional world we experience may be an illusion, a projection of a more fundamental, two-dimensional reality that exists on some distant cosmic screen. The most concrete and successful realization of this idea is the ADS-CFT correspondence, or gauge-gravity duality, discovered by the physicist Juan Maldacena in 1997. This is a remarkable mathematical conjecture that proposes an exact equivalence, a duality, between a theory of quantum gravity in a specific, five-dimensional, negatively curved spacetime called anti-de Sitter space, and a more conventional, lower-dimensional quantum field theory that lives on the four-dimensional boundary of that space. The two theories look completely different, but they are, according to the duality, just two different mathematical descriptions of the same underlying physical reality. Anything that happens in the five-dimensional gravitational bulk has a corresponding description in the four-dimensional non-gravitational boundary theory, and vice versa. This correspondence provides a powerful new tool for studying some of the deepest problems in physics. It allows us to translate difficult, unsolved problems in quantum gravity into more tractable and well-understood problems in quantum field theory. And it offers a potential holographic solution to the black hole information paradox. In the ADS-CFT correspondence, the evaporation of a black hole in the five-dimensional bulk is equivalent to a normal, unitary, information-preserving quantum process in the four-dimensional boundary theory. Since the two theories are just different descriptions of the same reality, and since information is conserved in the boundary theory, it must also be conserved in the bulk. The information that falls into the black hole is not lost. It is holographically encoded on the boundary, and it escapes with the Hawking radiation in a way that preserves unitarity. The holographic principle and the ADS-CFT correspondence are some of the most profound and powerful ideas to have emerged from theoretical physics in the last few decades. They suggest a radical new picture of reality, a world where space, time, and gravity may not be fundamental, but are emergent, holographic properties of a deeper, underlying quantum informational reality. While the correspondence has only been proven for a specific and rather unrealistic type of spacetime, it is a powerful proof of principle. It shows that a consistent quantum mechanical and holographic theory of gravity is possible. And it provides us with a new and deeply beautiful lens through which to view the universe. A lens that suggests that the ultimate secrets of the cosmos may not be written in the language of matter and energy, but in the subtle, quantum, and holographic language of information itself. The journey to understand the ultimate nature of reality, to find a single, unified theory that can describe all the forces and particles of nature, has led us to some of the most abstract and beautiful ideas in the history of science. From the vibrating strings of string theory to the quantum foam of loop quantum gravity, we are pushing the boundaries of our mathematics and our imagination. And yet, this quest is also a deeply empirical one, a quest that is constantly being guided, constrained, and inspired by the data we gather from our observations of the universe. We are living in a golden age of cosmology, a time of unprecedented observational power, a time when a new generation of telescopes and experiments is poised to answer some of the longest-standing questions in science, and to open up new, unforeseen windows onto the cosmos. The James Webb Space Telescope, with its giant golden eye, is already revolutionizing our view of the early universe, peering back in time to see the first galaxies and stars lighting up the cosmic darkness. The Vera C. Rubin Observatory, with its vast digital camera, will soon begin a decade-long survey of the southern sky, creating the deepest and most detailed movie of the universe ever made. A movie that will allow us to trace the history of cosmic expansion, to map the invisible scaffolding of dark matter, and to catch the fleeting glimmers of cosmic explosions. The Square Kilometer Array, a continent-spanning radio telescope, will map the three-dimensional structure of the cosmos by observing the faint, ancient radio waves from neutral hydrogen, giving us an unprecedented view of the cosmic dawn and the epoch of ionization. And the Laser Interferometer Space Antenna will take gravitational wave astronomy into space, allowing us to hear the gentle, low-frequency ripples in space-time from the mergers of supermassive black holes and, perhaps, from the very first, violent moments of the Big Bang itself. These are just a few of the incredible instruments that will shape the future of cosmology. They will provide us with a wealth of new data that will test our current theories to their breaking point, data that will challenge our assumptions, and data that will, undoubtedly, reveal new and unexpected puzzles. What is the nature of dark matter? What is the true identity of dark energy? Did cosmic inflation happen? And if so, how is our universe the only one? Or are we part of a vast cosmic multiverse? Is there life beyond Earth? These are the great open questions of our time, and we are, for the first time in human history, on the verge of being able to answer some of them with real, hard, scientific data. But the quest to understand the origin of the universe is more than just a scientific one. It is a deeply human one. It is a quest that is driven by our innate and perhaps unique capacity for wonder, for curiosity, for the desire to know our place in the grand cosmic scheme of things. It is a quest that connects us to our most ancient ancestors, who looked up at the same star-filled sky and asked the same fundamental questions. And it is a quest that has the power to unite us, to remind us of our shared cosmic heritage and of our common fragile home on this small blue planet. As we stand on the threshold of a new era of discovery, we are filled with a sense of both profound humility and exhilarating excitement. We are humbled by the vastness of the cosmos and the depth of our own ignorance, but we are also excited by the incredible power of the human mind to comprehend, to explore, and to understand. The journey is far from over. The greatest adventures, the most profound revelations may still lie ahead, waiting for us in the deep, silent, and beautiful darkness that lies just beyond the horizon of our current understanding. And as you close your eyes and let the universe of your own mind unfold in the quiet theater of your dreams, you can feel a sense of participation in this grand human adventure. The consciousness that is about to journey into the mysterious inner cosmos of sleep is the same consciousness that is, at this very moment, reaching out to the stars, listening for the echoes of creation, and striving to read the silent, beautiful, and endlessly fascinating story of the universe. Good night, and may your dreams be as vast and as wonderful as the cosmos itself. What if the key to time travel isn't hidden in the grandeur of massive spaceships or the elegant theoretical curves of a wormhole, but in a realm so small, so counterintuitive, that it forces us to question the very fabric of reality? A world where particles can be in two places at once, where they defy our expectations of cause and effect, and where they can communicate instantaneously across vast cosmic distances. Welcome to the quantum realm, the strange and beautiful foundation of modern physics, and perhaps our most promising path to unlocking the profound mysteries of time itself. Quantum physics is not just a theory about the bizarre behavior of the tiniest constituents of matter. It is a field that is teeming with possibilities, with phenomena so complex and so contrary to our everyday experience that they have fundamentally reshaped how we think about space, about matter, and, most tantalizingly, about time. Have you heard of quantum entanglement? The spooky action at a distance where two particles can remain mysteriously connected, their fates intertwined, no matter how far apart they are. Or have you contemplated the strange implications of retrocausality? The mind-bending idea that a choice made in the future could ripple backwards to influence an event in the past. These are not just concepts from the pages of science fiction. They are active areas of scientific inquiry, ideas that are pushing the boundaries of our understanding and hinting at the familiar linear rules of time we have always taken for granted might be just one limited perspective on a much deeper and far stranger reality. But time is not just an abstract scientific concept. It is the very rhythm of our lives, the relentless, forward-moving current that carries us from one moment to the next. Or does it? Could there be ways to slow it down, to speed it up, or even, perhaps, to reverse its flow entirely? The quantum realm, with its inherent uncertainty and its defiance of classical logic, introduces us to a world of bizarre and thrilling possibilities, from the potential to manipulate the very fabric of space-time to the exploration of alternate parallel realities. If you are ready to uncover how the strangest science of today could define the future of our relationship with time, then you are in for an exciting exploration. Together, we will break down the quantum mysteries that are reshaping our understanding of the universe, and we will venture into the incredible possibilities they offer. Welcome to this fascinating journey into the heart of quantum physics and the tantalizing dream of time travel. Time, as we experience it in the course of our lives, feels like a simple and straightforward concept. It is the steady, metronomic beat of an alarm clock that rouses us from sleep, the relentless ticking of seconds that turn into minutes, and minutes that turn into days. It is a seamless, linear progression, a universal ruler that we use to structure our existence, to measure our past, and to plan our future. But this intuitive, everyday experience of time as a steady and absolute march forward is a powerful illusion, a macroscopic simplification of a much more complex, more fluid, and more mysterious reality. To truly begin an exploration of time, we must first understand how our scientific conception of it has evolved. The classical view, most famously articulated by Isaac Newton, treated time as an absolute and universal constant. In the Newtonian universe, a single, master clock ticked at the same, unwavering rate for every object, in every corner of the cosmos. It was a fixed, unchanging background, a rigid stage upon which the drama of motion and force played out. But this comforting, clockwork picture of the universe was shattered in the early 20th century by Albert Einstein's theory of relativity. Einstein revealed that time is not absolute. It is relative. It is a dynamic and flexible dimension, inextricably woven together with space into a single, four-dimensional continuum called space-time. And this fabric of space-time is not a passive stage. It is an active participant in the cosmic drama, capable of being stretched, compressed, and warped by the presence of mass and energy. This warping of space-time is what we experience as the force of gravity. Time, in this relativistic picture, is a local phenomenon. The closer you are to a massive object, like a planet or a star, the more space-time is curved and the slower time flows. An atomic clock on a mountaintop will tick slightly faster than an identical clock at sea level. The astronauts on the International Space Station are aging a tiny fraction of a second slower than we are here on Earth. This effect, known as gravitational time dilation, is real and measurable. Similarly, the faster you move through space, the slower you move through time, a phenomenon known as velocity time dilation. A spaceship traveling at near the speed of light would experience time passing much more slowly than a stationary observer. For the astronauts on board, A journey that takes a few years could correspond to centuries or even millennia passing on Earth. Relativity revolutionized our understanding of time, transforming it from an absolute, universal constant into a dynamic, malleable dimension, intimately tied to the geometry of space and the motion of objects within it. But even this groundbreaking, relativistic view of time is now being challenged and deepened by the strange and often baffling world of quantum mechanics. Quantum mechanics throws a new and powerful wrench into our understanding of time, revealing a reality that is even more counterintuitive than the curved space-time of Einstein. At its core, quantum mechanics is a theory of probabilities and possibilities, not of certainties and definitive outcomes. The quantum realm is a hazy, indeterminate world, and this inherent ambiguity extends to the very nature of time itself. One of the foundational principles of quantum mechanics is the uncertainty principle. We often think of this in terms of position and momentum, but there is also a corresponding time-energy uncertainty principle. This principle suggests that the more precisely you try to measure the energy of a quantum system, the less precisely you can know the duration of that state, and vice versa, at the most fundamental subatomic level. Time is not a sharp, well-defined coordinate, but a fuzzy, blurred, and uncertain quantity. It is as if the universe, at its smallest scales, refuses to be pinned down to a single, definite moment. Another, even more profound. Quantum concept is superposition. A quantum particle, like an electron, can exist in a superposition of multiple, seemingly contradictory states at the same time, as long as it is not being measured. This raises fascinating, if highly speculative, questions about the nature of time. If a particle can be in a superposition of different locations or different energy states, could it, in some sense, be in a superposition of different moments in time? Could different timelines or different temporal possibilities coexist in a quantum state until a measurement collapses them into a single, experienced reality? While this is far from a mainstream scientific theory, it is the kind of mind-bending question that the strangeness of the quantum world forces us to ask. These quantum peculiarities provide the fertile ground from which new and often radical theories of time are beginning to emerge. One such idea is the block universe theory. This is a concept that has its roots in relativity, but it gains a new and deeper resonance in the context of quantum mechanics. In the block universe view, time is not a flowing river that carries us from a fixed past to an open future. It is a static, four-dimensional block of space-time, in which all of time past, present, and future exists simultaneously and equally. Your birth. This very moment you are reading these words, and all the events of the distant future are all equally real, all just different coordinates in this frozen, four-dimensional landscape. In this picture, the flow of time is a subjective illusion of our consciousness, a trick of our perception as our awareness moves through this pre-existing block. Another, even more radical, idea is that time, as we perceive it, may not be a fundamental aspect of reality at all. It could be an emergent property, a macroscopic phenomenon that arises from the deeper, more fundamental, and perhaps timeless interactions of the quantum world, in the same way that temperature emerges from the collective motion of countless individual atoms. In this view, at the most fundamental level of reality, there may be no before or after, no arrow of time, only a complex network of quantum relationships. The time we experience is a kind of statistical thermodynamic illusion, a consequence of the fact that we are large, complex, and entropy-producing systems. Finally, the phenomenon of quantum entanglement, the spooky action at a distance where two particles can remain instantaneously connected across vast stretches of space, adds another layer of mystery to the quantum time conundrum. If this non-local connection can link particles across space, could a similar form of entanglement link events across time? Could a measurement made on a particle today be entangled with the state of a particle in the distant past or future? This is a highly speculative and controversial area of research, but it is one that is being actively explored by some theoretical physicists. It hints at a universe where the relationship between past, present, and future is far more complex and interconnected than our classical intuition would ever allow. From the uncertainty of quantum measurements to the timelessness of the block universe, from the emergent nature of time to the temporal possibilities of entanglement. Quantum mechanics is not just challenging the simple, classical view of time. It is shattering it. And from the pieces, it is offering us the tantalizing clues to a new, deeper, and far more wondrous understanding of this most fundamental and most mysterious aspect of our reality. Imagine, for a moment, a particle approaching a solid wall. In our everyday classical world, the outcome is simple. If the particle does not have enough energy to break through or go over the wall, it will bounce off. The wall is an absolute barrier, but in the strange and counterintuitive world of quantum mechanics, this is not always the case. There is a small but non-zero probability that the particle can simply appear on the other side of the wall without having broken it and without having had enough energy to overcome it. This is the phenomenon of quantum tunneling. And it is not science fiction. It is a real, measurable, and essential feature of our universe. At its core, quantum tunneling is a direct consequence of the wave-like nature of quantum particles. A particle, like an electron, is not a solid, point-like object. It is a wave function, a cloud of probability that describes the likelihood of finding the particle at different locations. This wave does not stop abruptly at an energy barrier. It decays exponentially into it. If the barrier is thin enough, the wave function can have a small, but non-zero amplitude on the other side. This means that there is a finite probability that the particle, when measured, will be found on the far side of the barrier. Having seemingly tunneled through an impossible obstacle, it is as if the particle has momentarily borrowed the energy needed to overcome the barrier, thanks to the energy-time uncertainty principle passed through, and then repaid the energy on the other side. This unsettling, yet mesmerizing, behavior is not just a theoretical curiosity. It is a process that is happening all around us, and even within us. The sun shines because of quantum tunneling. In the immense heat and pressure of the sun's core, hydrogen nuclei are constantly colliding. Classically, they do not have enough energy to overcome their mutual electrostatic repulsion and get close enough to fuse together. But thanks to quantum tunneling, they have a small chance of bypassing this energy barrier, allowing the strong nuclear force to take over and initiate the process of nuclear fusion. It is this quantum leap that powers the sun and, ultimately, all life on Earth. Quantum tunneling is also at the heart of much of our modern technology. The transistors that are the building blocks of every computer and smartphone rely on the ability of electrons to tunnel through thin, insulating barriers in semiconductor materials. The flash memory that stores our data works by trapping and releasing electrons in a floating gate through a quantum tunneling process. Even some biological processes, like the way enzymes catalyze chemical reactions or the way our sense of smell works, are now thought to involve a form of quantum tunneling. The stark difference between the behavior of the quantum world and the macroscopic world of our everyday experience is a matter of scale and probability. While a single electron has a small but significant chance of tunneling through a thin barrier, a macroscopic object, like a basketball or a human being, is a collection of trillions upon trillions of particles. The probability of all of those particles tunneling through a solid wall at the same time is so infinitesimally, vanishingly small that it is, for all practical purposes. 0. We will never see a person walk through a wall, not because it is forbidden by the laws of physics, but because the odds are so astronomically against it that it would not happen even once in the entire lifetime of the universe. This scale-dependent nature of quantum effects is one of the reasons why the quantum world seems so strange and alien to us. Our intuition has been shaped by our experience in the macroscopic world, a world where probabilities have averaged out to become near certainties. But at the fundamental level, the universe is a game of chance, a world of probabilities and possibilities. Now, this is where the conversation turns towards the truly speculative and mind-bending. If a particle can tunnel through a barrier in space, could it, or perhaps the information it carries, tunnel through a barrier in time? This is a thrilling question that has captured the imagination of physicists and science fiction writers alike. While the concept of temporal tunneling is not a well-established scientific theory, it is the kind of what-if question that the strangeness of quantum mechanics invites us to ask. Could a particle tunnel from the present moment to a moment in the future? Bypassing the intervening time, could the information about a future event tunnel back to the present, giving us a form of precognition? These are ideas that are on the very fringes of theoretical physics, and they lack any experimental evidence. But they are born from a deep recognition of the parallels between space and time in modern physics. In Einstein's relativity, space and time are unified into a single, four-dimensional space-time. If quantum tunneling is possible in the spatial dimensions, it is not entirely illogical to ask if a similar phenomenon could be possible in the temporal dimension. For now, the boundary between science fact and science fiction remains clear. Quantum tunneling is a real, observed, and technologically crucial phenomenon that governs the behavior of particles in space. Its potential connection to time travel remains a purely hypothetical and deeply fascinating speculation. But the very existence of a phenomenon like quantum tunneling, a phenomenon that so profoundly violates our classical intuition, should give us a sense of humility. It is a powerful reminder that our everyday understanding of the world is a limited one, and that the universe, at its deepest level, operates according to a set of rules that are far stranger, more subtle, and more wondrous than we can yet fully comprehend. It is a call to keep questioning, to keep exploring, and to remain open to the possibility that the universe still holds secrets that could one day turn our most cherished scientific and philosophical assumptions on their head. Could a decision you make today ripple backwards through time to influence an event that has already happened? This is a question that seems to belong to the realm of paradox and fantasy. And yet, it is a question that physicists are forced to confront when they grapple with the strange and beautiful implications of delayed choice experiments in quantum mechanics. This is not about time travel in the classical sense of rewriting history. It is about something far more subtle and perhaps even more profound. It is about the strange and seemingly retroactive way in which our choices as observers appear to shape the reality of the quantum world. The story begins with the famous double-slit experiment. As we have seen, a single quantum particle, like a photon, will behave like a wave and create an interference pattern if we do not know which of the two slits it has passed through. But if we place a detector at one of the slits to gain this which path information, the photon behaves like a particle, and the interference pattern disappears. The act of measurement changes the outcome. In the 1970s, the brilliant and iconoclastic physicist John Archibald Wheeler proposed a thought experiment that took this strangeness to a whole new level. He asked, what if we delay the choice of whether or not to measure the which path information until after the photon has already passed through the slits? Imagine a setup where the photon has already gone through the double-slit barrier and is on its way to a detector screen. At the last possible moment, We can choose to either insert a set of detectors that will tell us which path the photon took, or to remove them and allow the interference pattern to form. Classical intuition would tell us that this choice should make no difference. The photon has already passed through the slits. Its behavior, whether wave-like or particle-like, should already be a fixed, historical fact. But this is not what happens. When Wheeler's thought experiment and its various more sophisticated versions have been carried out in real laboratories, the results have been consistently jaw-dropping. Even when the choice of measurement is made after the photon has passed through the slits, the outcome is the same. If the detectors are inserted, the photon is found to have behaved like a particle. If the detectors are removed, the photon is found to have behaved like a wave. It is as if the photon, in its journey, somehow knew what choice the experimenter was going to make in the future, and adjusted its past behavior accordingly. This is a result that is so counterintuitive that it can make one's head spin, but it is crucial to understand what it does, and does not mean. Delayed choice experiments do not imply that we can send information back in time, or that we can literally change the past. There is no paradox, no violation of causality. The trick lies in the subtle and holistic nature of quantum measurement. A quantum system, like our photon, is not a classical object with pre-existing properties. It is a wave function, a cloud of possibilities, and the reality we perceive is only defined in the context of the entire experimental setup, including the final act of measurement. The behavior of the photon is not an intrinsic property that it carries with it on its journey. Its waviness or particleness is a property of the whole system, of the relationship between the particle and the measuring device. To ask what the photon was doing before the final measurement is to ask a question that, from a quantum perspective, may not have a well-defined answer. As Wheeler himself famously put it, no elementary phenomenon is a real phenomenon until it is an observed phenomenon. The past at the quantum level is not a fixed and unchangeable record. It is an open, probabilistic story that is only finalized, only brought into being by the observations we make in the present. This is a profound and deeply unsettling idea. It challenges our most basic, classical understanding of time and causality. We are used to thinking of time as a linear sequence, where a cause in the past leads to an effect in the future, but the quantum world seems to hint at a more complex and more intertwined relationship between the past, the present, and the future. Some physicists, in trying to make sense of these results, have been led to entertain the radical idea of retrocausality, the notion that influences can, in some subtle quantum mechanical way, travel backwards in time. This is not about sending signals, but about a more fundamental, and as yet not fully understood, temporal symmetry in the laws of nature. The choices we make now may be part of a larger, self-consistent loop of causality that includes both the past and the future. But even without resorting to such radical ideas, the delayed choice experiment serves as a powerful reminder of the fundamental weirdness of the quantum world. It is a world where our common-sense notions of reality, of locality, and of time itself break down. And this has practical implications. The deep understanding of quantum measurement that has come from grappling with these paradoxes is essential for the development of quantum technologies. Quantum computers, for example, are built on our ability to precisely control and manipulate the delicate, superpositional states of qubits. The delayed choice experiment is a powerful tool for probing the very nature of this quantum state, for understanding how it is created, how it evolves, and how it is collapsed by the act of measurement. It is a mind-bending exercise in quantum logic, to be sure, but it is also a testament to the power of human curiosity, to our relentless drive to ask the deepest questions, and to our willingness to follow the evidence, even when it leads us into a reality that is far stranger, more subtle, and more beautiful than our classical minds could have ever imagined. The delayed choice experiment reveals the strange, retroactive influence of observation on a quantum system. But what if we could go a step further? What if we could not just decide whether to observe, but could also decide to forget what we have observed? This is the tantalizing premise of the quantum eraser experiment, one of the most bewildering and philosophically profound concepts in all of quantum mechanics. It is an idea that seems to be pulled directly from the pages of a science fiction novel, an experiment where the simple act of erasing information seems to rewrite a reality that has already happened. The story begins, once again, with the double-slit experiment. We know that if we measure which slit a photon goes through, we gain which path information, and this act of measurement destroys the wave-like interference pattern. The photon behaves like a particle. The quantum eraser experiment asks a simple, but audacious, question: what if we could erase this which path information after we have recorded it? Could we bring the interference pattern back from the dead? The setup for a delayed choice quantum eraser experiment is ingenious and complex. It typically involves a source that produces pairs of entangled photons. These photons are linked in such a way that they are a single, unified quantum system, even if they travel in different directions. One photon, the signal photon, is sent towards a double-slit barrier and a detector screen. The other photon, the idler photon, is sent along a different path to a separate set of detectors. The clever part is that the path of the idler photon can be used to determine which slit its entangled partner, the signal photon, went through. So, by measuring the idler photon, we are, in effect, measuring the which path information of the signal photon, even without directly interacting with it. And as expected, when we do this, the signal photons hitting the screen do not show an interference pattern. They behave like particles. But now comes the eraser part. The experiment is set up in such a way that we can make a choice about what to do with the idler photon. We can either measure it in a way that reveals the which path information, or we can erase this information by sending the idler photon through a set of beam splitters that scrambles its path, making it impossible to know which slit its entangled partner went through. And here is the truly mind-bending twist. This choice of whether to erase the information can be made after the signal photon has already hit the detector screen. And when the experiment is performed, the results are stunning. If we look at the total pattern of all the signal photons on the screen, it is just a diffuse blob with no interference. But if we then look at our data and select only those signal photons whose entangled idler partners had their which path information erased, a beautiful, clear interference pattern magically reappears. It is as if the future act of erasing the information has reached back in time to influence the past behavior of the signal photons, causing them to act like waves. At first glance, this seems to be a clear violation of causality, a form of retroactive rewriting of history. But as with all quantum paradoxes, a closer look reveals a more subtle and even more profound truth. The quantum eraser does not actually allow us to change the past. The key lies in the process of post-selection and the nature of entanglement. The interference pattern is not visible in the raw, total data. It is only revealed when we correlate the data from the signal photons with the data from the idler photons. It is a hidden pattern, a ghostly correlation that is only brought to light when we have the information from both parts of the entangled system. The choice we make in the future about the idler photon does not change what has already happened at the signal detector. It simply changes the way we are able to sort and interpret that past data to reveal a hidden, pre-existing quantum correlation. The story is self-consistent across time. There is no paradox. But the philosophical implications are still staggering. The quantum eraser experiment is a powerful demonstration of the holistic and non-local nature of quantum reality. It shows that an entangled system is a single, indivisible whole, and that its properties cannot be understood by looking at its parts in isolation. The behavior of the signal photon is inextricably linked to the fate of its distant, entangled twin, and the reality of the system is only fully defined when we consider the entire experimental setup, including the final measurements made on both particles. It is also a profound illustration of the deep connection between information and physical reality in the quantum world. The presence or absence of which path information is not just a matter of our knowledge. It is a physical variable that has a direct and tangible effect on the behavior of the system. To erase information is not just a mental act. It is a physical act that can restore the wave-like, superpositional nature of a quantum system. The possible applications of this principle, while still largely theoretical, are tantalizing. The quantum eraser provides a powerful tool for exploring the fundamental nature of quantum measurement and decoherence, which is crucial for the development of robust quantum computers, the ability to control and manipulate quantum information. To erase it and to restore quantum coherence could be a key ingredient in building fault-tolerant quantum memory and communication systems. But beyond any potential technological applications, the quantum eraser holds a deep and enchanting allure. It is a cosmic magic trick, a demonstration of the universe's ability to operate in ways that are far more subtle, strange, and interconnected than our classical minds could have ever conceived. It is a crack in our familiar worldview, a window into a deeper, more holistic, and more mysterious reality. A reality where the past, the present, and the future are bound together in a beautiful and paradoxical quantum dance. What if the familiar one-way street of time, the relentless march from cause to effect, is not a fundamental law of the universe, but a macroscopic illusion? What if, at the deepest level of reality, the future can ripple backwards to influence the past? This is the radical and mind-bending concept of retrocausality, an idea that is so counterintuitive that it seems to belong to the realm of fantasy, but which is being seriously considered by some physicists as a potential way to resolve some of the deepest paradoxes of quantum mechanics. At its core, retrocausality challenges our most basic and most cherished assumption about the nature of time, that causation is a one-way street. In our everyday world, events unfold in a clear, linear sequence. You drop a glass, and then it shatters. The cause precedes the effect. The idea that the shattering of the glass could somehow influence the act of dropping it is absurd. But in the strange, probabilistic world of the quantum, the rules of cause and effect are not so clear-cut. Retrocausality proposes that the relationship between events is not a simple, forward-moving chain, but a more complex, self-consistent loop, where influences can travel both forwards and backwards in time. This is not about sending messages to the past to change history. It is about a more subtle and more fundamental temporal symmetry in the laws of nature, a symmetry that is hidden from us in our macroscopic world, but which may be at play in the quantum realm. The idea of retrocausality has its roots in some of the earliest debates about the nature of quantum mechanics. It was proposed as a way to explain the spooky action at a distance of quantum entanglement without violating the principle of locality. In a retrocausal picture, when you measure one of a pair of entangled particles, you are not instantaneously influencing its distant partner. Instead, your measurement choice sends an influence back in time to the moment when the particles were first entangled, and this influence then travels forward in time with the other particle, ensuring that its measurement outcome will be correlated with yours. It is a strange and seemingly convoluted explanation, but it is one that can, in principle, reproduce all the predictions of quantum mechanics without any faster-than-light communication. More recently, retrocausality has found a new and fascinating playground in the context of the delayed choice and quantum eraser experiments. As we have seen, these experiments seem to show a future measurement choice, retroactively determining the past behavior of a particle. While these results can be explained without invoking retrocausality, by appealing to the holistic and non-local nature of the quantum state, a retrocausal interpretation offers a different, and for some, a more intuitive, way of thinking about the problem. It takes the apparent retroactivity at face value. The choice made by the experimenter in the future sends a real physical influence back in time to the double-slit barrier, telling the particle whether to behave as a wave or a particle. The past, in this picture, is not a fixed and unchangeable record. It is a pliable, dynamic entity that is constantly being shaped by its relationship with the future. It is crucial to emphasize that retrocausality, as it is currently understood, does not allow for the kinds of paradoxes that are so beloved of science fiction. You cannot send a message back in time to tell yourself the winning lottery numbers, or to warn your past self not to make a terrible mistake. The influences are thought to be at the level of the quantum wave function, shaping the probabilities of events, not determining their specific outcomes in a controllable way. The universe, in a retrocausal model, is still self-consistent. The future can influence the past, but only in a way that is consistent with the present. It is a closed, logical loop. The grandfather paradox, for example, is avoided because the universe would simply not allow for a self-contradictory history to be created. If you were to travel back in time to try and prevent your own birth, the retrocausal influences would conspire to ensure your failure. The gun would jam, the car would break down, your resolve would fail. The timeline is robust. This is a concept that is incredibly difficult to test experimentally. The influences are subtle, and they are woven into the very fabric of quantum probability. But theoretical physicists are actively working on developing new experimental protocols that could distinguish between a standard, forward causal quantum mechanics and a retrocausal one. The practical applications of retrocausality, if it is a real feature of our universe, are, at this stage, purely in the realm of speculation, but the philosophical implications are profound. It would mean that our understanding of time, of causality, of free will, and of the relationship between the past, the present, and the future would need to be fundamentally rewritten. It would suggest a universe that is not a linear, unfolding story, but a single, holistic, four-dimensional block of space-time, in which all of time exists at once, and the connections between events are not limited to a single, forward-moving direction. It would be a universe where the future is not just a passive consequence of the past, but is an active participant in its creation. The pursuit of these answers is more than just an intellectual exercise. It is a testament to the human capacity to question what once seemed unquestionable, to imagine realities that are far beyond our everyday experience, and to relentlessly probe the deepest and most fundamental mysteries of existence. Retrocausality is a bold and delicate idea, a whisper from the frontier of physics that hints at a universe that is far more strange, more interconnected, and more wondrously complex than we have ever dared to imagine. Quantum physics often feels like a puzzle that you can't quite finish. Each piece seems to promise a glimpse of a larger, coherent picture, but the edges never quite seem to align. For decades, one of the most confounding aspects of the theory has been the measurement problem, the question of what happens when we observe a quantum system, when the ghostly probabilistic world of superposition collapses into a single, definite reality. The traditional Copenhagen interpretation simply posited that this collapse happens without explaining how or why. This was a deeply unsatisfying state of affairs for many physicists. Then, in the 1950s, a young doctoral student at Princeton named Hugh Everett III came along with a proposal that was as audacious as it was elegant. He suggested that the collapse never happens. The quantum wave function, with all its superpositional possibilities, is the complete and final description of reality. And when a quantum event with multiple possible outcomes occurs, the universe itself splits into multiple parallel universes, one for each possible outcome. This is the many worlds interpretation of quantum mechanics, and it is an idea that, if true, would completely and utterly transform our understanding of reality. Imagine flipping a coin. In the many worlds view, the very act of flipping the coin does not lead to a single outcome of heads or tails. It leads to a branching of reality. A universe is created where the coin lands heads and another equally real. Universe is created where it lands tails. You, the observer, also split. One version of you sees the heads and another version sees the tails, and each version is completely unaware of the other's existence. In this picture, the entire history of the universe is a constantly branching tree of possibilities, a multiverse of parallel realities, where every quantum choice, every probabilistic event, has led to the creation of a new world. The implications of this theory are breathtaking, and for many, deeply unsettling. It means that for every decision you have ever made, there is another version of you in a parallel universe who made the opposite choice. There is a universe where you took that job you turned down, a universe where you married your high school sweetheart, a universe where you caught that train you missed. Somewhere out there, in the vast branching landscape of the multiverse, all of your unlived lives are being lived out by other, equally real versions of yourself. It is an idea that is both exhilarating and dizzying, one that challenges our most basic assumptions about our own uniqueness and the nature of our own personal history. But how does this strange and wonderful idea of a branching parallel reality change our understanding of an even stranger concept? Time travel. The many worlds interpretation offers a beautiful and elegant solution to one of the most famous and intractable paradoxes of time travel. The grandfather paradox. The paradox, in its classic form, goes like this: if you were to build a time machine, travel back to the past, and prevent your own grandfather from meeting your grandmother, then your parent would never be born, and therefore you would never be born. But if you were never born, how could you have traveled back in time to commit the act in the first place? It is a logical contradiction that seems to make any form of time travel that can alter the past a physical impossibility. But in the many worlds interpretation, this paradox simply dissolves. When you travel back in time, you are not traveling into the past of your own specific branch of the multiverse. You are, in effect, crossing over into a different branch. When you interfere with the past in this new branch by, for example, preventing your grandfather from meeting your grandmother, you are not changing your own history. You are simply creating a new timeline, a new branch of the multiverse, one in which you were never born. But your original universe, the one from which you departed, remains completely unchanged. The version of you that built the time machine still exists, still has a grandfather, and still has a history. You have not erased yourself from existence. You have simply become a visitor, an orphan of time, in a parallel reality. The grandfather paradox is resolved because the cause and the effect are now in two separate, non-communicating universes. This makes time travel, at least in a theoretical sense, a much less dangerous and more self-consistent proposition. It is not an act of rewriting a single sacred timeline, but an act of exploring the vast, pre-existing landscape of parallel realities. It is less like editing a document and more like choosing to read a different book. But the many worlds interpretation, for all its elegance, does not come without its own set of challenges and complexities. For one, Can we still call it time travel if you can never return to your original timeline? If every trip to the past is a one-way ticket to a new, alternate reality, then the very concept of returning to your own time becomes meaningless. And how would you navigate this infinite, branching tree of possibilities? If you wanted to travel to a specific past event, how would you pinpoint the exact branch of the multiverse you wanted to visit? The sheer, incomprehensible vastness of the possibilities, while exciting, also makes the idea of a controlled, targeted form of time travel seem dauntingly, if not infinitely, complex. And of course, the biggest challenge of all is the fact that the many worlds interpretation, like the broader concept of the multiverse, is at present unfalsifiable. We have no way to experimentally verify the existence of these other parallel universes. They remain, for now, beautiful and compelling mathematical constructs, born from the strange logic of quantum mechanics, but not yet a part of our confirmed empirical reality. And yet, the many worlds interpretation continues to be a popular and influential idea among many theoretical physicists. It is a testament to the profound and often uncomfortable places that our science can lead us. It is an invitation to confront the very limits of our own understanding, to reconsider everything we think we know about the nature of time, of choice, of identity, and of existence itself. It is a mind-expanding lens through which to view the universe, a lens that reveals a reality that is not a single, linear story, but an infinite, branching, and wondrously complex tapestry of all possible stories. And it is a reminder that, in the strange and beautiful world of quantum physics, the line between science and science fiction is often a very thin and very blurry one indeed. Imagine a world where time is not a linear, unyielding arrow, where the future does not just follow the past, but can loop back to influence it, where the very boundaries of causality blur into a surreal and beautiful dance. This is not the opening to a fantastical novel, but the foundation of a real and mind-bending concept in theoretical physics, the closed timelike curve, rooted in the elegant but often strange equations of Einstein's general theory of relativity. These theoretical pathways propose that the fabric of space-time may not be a simple, flat sheet, but can, under certain extreme conditions, bend and fold back on itself, creating loops in time. While the idea has its foundations in the classical, deterministic world of Einstein, its profound and paradoxical implications find their most fascinating expression when they intersect with the strange, probabilistic rules of the quantum realm. Today, we will explore this fascinating intersection, focusing on the scientifically grounded theories that are pushing the boundaries of our understanding of time, and offering us a tour through a universe that is far stranger and more compelling than any science fiction script. Closed timelike curves, or CTCs, first emerged as a possibility from certain exact solutions to Einstein's field equations. These equations describe how the presence of mass and energy curves the geometry of space-time. In most familiar situations, this curvature is gentle, leading to the familiar, forward-moving flow of time. But in some exotic and highly theoretical scenarios, the curvature can become so extreme that it creates pathways that loop back into their own past. Imagine tracing a path through the 4 dimensions of space-time that brings you back to your starting point, not just in space, but in time as well. This is a closed timelike curve. One of the first and most famous of these solutions was discovered by the brilliant logician and mathematician Kurt Gödel in 1949. He found that in a universe that is rotating as a whole, it would be possible for a sufficiently fast-moving spaceship to travel on a path that would return it to its own past. Later, The physicist Frank Tipler explored the theoretical construct of a Tipler cylinder, an infinitely long and incredibly dense, rotating cylinder, which could also, in theory, generate CTCs around it. These models, while mathematically sound, are thrilling for the imagination, but they also raise profound questions about whether nature would ever allow such structures to form. They require conditions a rotating universe, an infinite cylinder that do not seem to correspond to the cosmos we observe. But beyond their theoretical elegance, closed time-like curves force us to confront the great paradoxes of time travel. If such a pathway through time exists, could an object or a person journey into their own past? This possibility immediately opens the door to the grandfather paradox, a time traveler who goes back and interferes with the past in a way that prevents their own existence. For example, by preventing their grandparents from ever meeting, creates a logical contradiction that seems to make such a journey impossible. For a long time, this was seen as a powerful argument against the physical possibility of time travel. And yet, the mathematics of general relativity does not explicitly forbid the existence of CTCs. This has left physicists to grapple with a deep and perplexing question: do these paradoxes represent a fundamental flaw in our understanding of time? Or is there a deeper, and perhaps quantum principle at play that resolves them? The creation of a closed time-like curve, even in theory, is not a simple matter. The mathematical models that allow for them typically require the existence of exotic matter, a hypothetical form of matter with a negative energy density. This is a substance that would have bizarre anti-gravitational properties. And it is something that has never been observed in nature, while some subtle quantum phenomena, like the Casimir effect, can create localized regions of negative energy. The existence of a macroscopic, stable form of exotic matter remains highly speculative and may be forbidden by the fundamental laws of physics. The energy requirements to warp space-time into a loop are also astronomically high, far beyond anything our current, or even foreseeable, technology could ever achieve. But this is where the strange and beautiful world of quantum mechanics offers a new and intriguing avenue of exploration. Unlike the deterministic framework of classical physics, where an object has a single, definite history, the quantum world is a realm of probabilities and uncertainties. This has led some physicists to propose that the paradoxes of time travel might be resolved, not by forbidding CTCs, but by applying the rules of quantum mechanics to them. This is the idea of quantum self-consistency. In a quantum model of a CTC, a particle traveling on a time loop does not have a single, classical trajectory. It has a wave function, a superposition of all possible histories. The principle of self-consistency, most famously formulated by the physicist David Deutsch, proposes that the only histories that are allowed are those that are self-consistent. The particle can interact with its own past, but only in a way that does not create a logical contradiction. For example, in a quantum version of the grandfather paradox, a particle sent back in time to flip a switch that would prevent its own creation would not have a definite outcome. It would exist in a superposition of states, and the probabilities of the different outcomes would adjust themselves in such a way that no paradox is created. The probability of the particle successfully flipping the switch would be exactly balanced by the probability of it failing, leading to a self-consistent, if probabilistic, solution. This is an elegant and deeply quantum way of resolving the paradoxes. It suggests that the universe has a built-in, probabilistic censorship mechanism that prevents logical contradictions from ever occurring. Researchers have even begun to test these ideas using quantum computers to simulate the behavior of a qubit traveling on a closed time-like curve. These simulations have confirmed the predictions of Deutsch's model, showing that a self-consistent solution can always be found without any need to invoke a paradox. What's even more fascinating is that these simulations have shown that a qubit interacting with its past self through a CTC can gain extraordinary computational power, allowing it to solve certain problems that are thought to be intractable for even a standard quantum computer. This has led to the speculative, but tantalizing, idea that nature might be using the logic of closed timelike curves at some deep, hidden level of reality. As captivating as these ideas are, it is crucial to remember the immense challenges that lie ahead. To date, there is no experimental evidence for the existence of closed timelike curve. The exotic solutions of general relativity that contain them remain mathematical curiosities, tied to highly specific and often physically unrealistic conditions. Our technological capacity to manipulate space-time, which would require the harnessing of exotic matter or the generation of cosmic-scale energies, is nowhere near what would be needed to create a time loop in the laboratory. And even within the realm of quantum mechanics, while the simulations are intriguing, the practical implementation of a system that could genuinely send a particle on a journey into its own past remains light years away. These considerations underline a humbling truth about our current understanding. We are like children, just beginning to learn the alphabet of a deep and complex cosmic language. But in the gaps of our knowledge, in the tension between the classical and the quantum, lies the source of our greatest inspiration. The study of closed timelike curves is more than just an ambitious quest to build a time machine. It is a powerful intellectual tool that forces us to rethink the fundamental laws that govern space, time, and causality. It compels us to confront the deep and unresolved conflict between the deterministic, geometric world of Einstein and the probabilistic, superpositional world of the quantum, and in doing so, it is pushing the boundaries of human knowledge, unlocking profound new insights into the very nature of reality itself. Whether through the refinement of our theories of general relativity, the advancement of quantum computation, or the revolutionizing of our cosmological models, the research into closed timelike curves is creating ripples that are felt across multiple disciplines, shaping the trajectory of scientific discovery for generations to come. Each new exploration, each new thought experiment, brings us a little closer to answering the foundational questions that have defined the human quest for understanding for millennia. And it is a bold and beautiful reminder of the audacity, the creativity, and the enduring wonder that lies at the very heart of the scientific exploration of the cosmos. The dream of time travel, of breaking free from the linear confines of our own existence, has been a powerful and persistent theme in human culture for centuries. But could this dream ever move from the realm of fiction into the world of scientific fact? While the idea of building a macroscopic time machine remains firmly in the realm of speculation, some of the most advanced and mind-bending theories in modern physics are beginning to provide a theoretical and perhaps even a quantum blueprint for how such a feat might one day be possible. The journey begins with the strange and beautiful geometry of space-time, as described by Einstein's theory of general relativity. As we have seen, this theory allows for the theoretical possibility of wormholes, or Einstein-Rosen bridges, hypothetical tunnels through the fabric of space-time that could connect two very distant locations, or even two different moments in time. The problem is that these cosmic shortcuts are predicted to be incredibly unstable, collapsing in on themselves almost instantly. To keep a wormhole open long enough for something or someone to pass through would require a form of exotic matter, a substance with a negative energy density that could prop open the throat of the wormhole, counteracting the immense gravitational forces that are trying to crush it. For a long time, this was seen as a fatal flaw in the idea of traversable wormholes. But the quantum world, with its strange and counterintuitive rules, may offer a solution. At the heart of quantum mechanics lies the concept of quantum fluctuations, the incessant energetic ripples that occur even in a perfect vacuum. These fluctuations, a direct consequence of the uncertainty principle, can give rise to localized regions of negative energy. The Casimir effect is a direct, experimental demonstration of this phenomenon. While the amount of negative energy produced in the Casimir effect is tiny, it proves that the concept is not just a mathematical fantasy. The challenge, then, is to find a way to generate and control a sufficient amount of this quantum negative energy to stabilize a macroscopic wormhole. This is a technological hurdle of almost unimaginable proportions, but it is one that has shifted the problem from a matter of fundamental physical impossibility to a matter of extreme, but perhaps not insurmountable, engineering. This is where the power of quantum computing may one day come into play. Quantum computers, with their ability to simulate complex quantum systems, are becoming an essential tool for exploring the strange and wonderful world of quantum gravity. They allow researchers to model the curvature of space-time, the behavior of quantum fields in extreme gravitational environments, and the very nature of the quantum vacuum itself. As these machines become more powerful, they may allow us to test our theories of wormhole stability and to explore the properties of exotic matter in a virtual computational laboratory. This could lay the theoretical groundwork for understanding how to manipulate spacetime in a controlled and predictable way. Another, even more speculative, but equally fascinating, quantum phenomenon that could have implications for time travel is the time crystal. A regular crystal, like a diamond or a snowflake, is a structure whose atoms are arranged in a repeating pattern in space. A time crystal. A concept first proposed by the Nobel laureate Frank Wilczek in 2012 is a structure whose lowest energy state is one in which the constituent particles are in a periodic, repeating motion. It is a system that spontaneously breaks time translation symmetry. In a sense, it has a built-in perpetual clock. What is truly remarkable is that this perpetual motion does not require any input of energy and does not violate the laws of thermodynamics, as it occurs in the system's ground state. The existence of time crystals was experimentally confirmed in 2016, a stunning demonstration of a new and exotic state of matter. The practical applications of time crystals are still being explored, but they could have profound implications for quantum computing, for high-precision timekeeping, and perhaps even for our understanding of the nature of time itself. Could a time crystal, with its stable, repeating temporal loop, be used to anchor or stabilize a closed timelike curve? Could it be used to create a localized region of spacetime where the normal linear flow of time is disrupted? These are ideas that are on the very edge of theoretical physics, but they are a beautiful example of how the discovery of new, exotic quantum phenomena can open up entirely new avenues of thought. Finally, the strange, non-local connection of quantum entanglement may offer yet another, and perhaps the most profound, pathway to rethinking our relationship with time. The EREPR conjecture, a bold and beautiful idea proposed by physicists Leonard Susskind and Juan Maldatina, suggests a deep and unexpected equivalence between two of the strangest concepts in modern physics, quantum entanglement and wormholes. The conjecture posits that every pair of entangled particles is, in some deep, geometrical sense, connected by a microscopic wormhole. This is a mind-bending idea, one that suggests that the strange, non-local connection of entanglement is not a spooky, disembodied action at a distance, but has a real, physical and geometrical manifestation in the structure of space-time itself. It suggests a deep unity between the laws of quantum mechanics and the laws of general relativity. A hint that these two great theories are just two different descriptions of the same, underlying reality. Does this mean we can use entanglement to travel through wormholes? Not in any simple sense. The wormholes in the EREEPR conjecture are thought to be non-traversable. But the idea that the very fabric of spacetime is woven from the threads of quantum entanglement is a revolutionary one. It suggests that if we could learn to manipulate and control large-scale, multi-particle entanglement, we might, in effect, be learning to manipulate and control the geometry of spacetime itself. This is the ultimate, and perhaps the most ambitious frontier in the quest for a quantum time machine. It is a quest that is no longer just about building bigger spaceships or finding cosmic shortcuts. It is about understanding and harnessing the deepest, most fundamental, and most mysterious properties of the quantum world itself. It is a journey that will require leaps of imagination, of experimental ingenuity, and of theoretical brilliance. And it is a journey that, whether it ultimately succeeds in building a time machine or not, is already transforming our understanding of the universe, and our own. Strange and wonderful place within it. The dream of traveling through time, of breaking the chains of the linear present, has long been a powerful and enduring part of the human imagination. But could this dream ever be more than just a dream? Could the strange and beautiful laws of quantum mechanics provide a key to unlocking the mysteries of time itself? The phenomenon of quantum entanglement, the spooky action at a distance that so perplexed Einstein, lies at the very heart of this inquiry. Entanglement describes a profound and mysterious connection between two or more particles, a bond so deep that their fates remain intertwined. No matter how far apart they are separated in space, a measurement on one particle instantly influences the state of the other. For a long time, this was seen as a bizarre, but ultimately limited, feature of the quantum world. A strange correlation that could not be used to send information faster than light. But in recent years, a new and radical idea has emerged, one that suggests that this spooky connection may have a deep and unexpected relationship with the very geometry of space-time. This is the EREEPR conjecture, a bold and beautiful hypothesis that proposes a fundamental equivalence between quantum entanglement and wormholes. It is an idea that suggests that every pair of entangled particles is connected by a tiny, microscopic wormhole, a shortcut through the fabric of spacetime. This is not to say that we can simply entangle two particles and then crawl through the wormhole that connects them. The wormholes in the EREEPR conjecture are thought to be non-traversable. They are more like a private, quantum information channel than a physical tunnel. But the conjecture itself is revolutionary. It suggests that the strange, non-local connectivity of the quantum world and the dynamic geometric structure of the relativistic world are not two separate things, but are two different descriptions of the same underlying reality. The very fabric of space-time in this picture may be woven from the threads of quantum entanglement. The universe is not a classical, geometric stage upon which a quantum drama plays out. The stage and the actors are one and the same. This has profound implications for our understanding of time. If the geometry of space-time is emergent from the quantum state of the universe, then time itself may be an emergent phenomenon, a property that arises from the complex web of entanglements that connect all the particles in the cosmos. This could provide a new way to think about the arrow of time, the forward flow of time. The increase of entropy may be related to the increasing complexity of the entanglement structure of the universe as it evolves. And it opens up the tantalizing, if highly speculative, possibility that by manipulating entanglement, we could, in a sense, be manipulating the structure of time itself. The EREEPR conjecture is still a theoretical idea, one that is on the cutting edge of research in quantum gravity. But the connection between entanglement and spacetime is not just a matter of abstract theory. It is being probed in real and increasingly sophisticated laboratory experiments using quantum processors, the powerful new machines that can control and manipulate the quantum states of individual particles. Scientists are now able to simulate the behavior of quantum systems in curved space-time, and even to create laboratory analogs of wormholes and black holes. In one groundbreaking experiment, researchers at Google, in collaboration with physicists at Caltech, used their Sycamore quantum processor to create a simulation of a traversable wormhole. They did this by creating a highly entangled state between two sets of qubits on their chip and then sending a quantum signal from one set to the other. They found that the signal propagated in a way that was consistent with the signal having traveled through a wormhole in a holographic toy model of a universe. This was not a real wormhole in physical space. Of course, it was a simulation, a quantum computation. But it was a stunning demonstration of the deep connection between the mathematics of quantum entanglement and the physics of space-time geometry. It was the first experimental realization of the idea that the dynamics of a gravitational system can be emergent from the quantum information processing of a non-gravitational one. These are early days, and the technological challenges are immense. Creating and maintaining the large-scale, highly entangled quantum states needed to test these ideas with precision is a colossal experimental hurdle. The fragility of quantum coherence, its susceptibility to decoherence from the surrounding environment, is a constant battle for quantum engineers. But the progress is rapid. And as our quantum technologies become more powerful, as we learn to control and manipulate the strange and beautiful world of entanglement with ever greater precision, we will be able to probe these deep connections between the quantum and the cosmos in new and profound ways. The potential implications are too enticing to ignore. If the link between entanglement and space-time is a real physical feature of our universe, could we one day learn to harness it? Could we create and stabilize a macroscopic, traversable wormhole by creating a specific, highly entangled state of matter and energy? Could we use the non-local connections of entanglement to create shortcuts, not just through space, but through time? These are questions that are on the very edge of our current scientific understanding. They are questions that may not be answered in our lifetimes. But they are questions that are no longer confined to the realm of science fiction. They are being asked and explored in the laboratories and on the blackboards of some of the world's leading physicists. The quest to understand the link between quantum entanglement and space-time is one of the most exciting and ambitious frontiers in all of science. It is a quest that promises to unify our two great theories of the universe, and in doing so, to reveal a reality that is far deeper, more mysterious, and more wondrously interconnected than we have ever dared to imagine. The idea of traveling backwards in time, of revisiting the past, is a concept that is fraught with paradox. The infamous grandfather paradox, in which a time traveler alters the past in a way that prevents their own existence, has long been seen as a fundamental, logical barrier to any form of time travel that can change history. But the strange, probabilistic nature of the quantum world may offer a way out, a way to have time travel without the paradoxes. This is a concept that is now being explored, not just in thought experiments, but in real laboratory simulations using some of the most advanced quantum computers in the world. Imagine a particle, a single qubit, traveling on a closed timelike curve, a path through space-time that loops back into its own past. In a classical world, this would be a recipe for paradox. If the particle is sent back in time to flip a switch that prevents it from ever being sent, we have a logical contradiction. But in the quantum world, the particle is not a classical object with a definite state. It is a wave function, a superposition of all its possible states. And according to the self-consistency principle proposed by David Deutsch, the only histories that are allowed on a CTC are those that are self-consistent. The universe, in a sense, edits out the paradoxes. Quantum simulations of this process, carried out by teams at IBM and Google using their powerful quantum processors, have shown how this can work in practice. They have successfully modeled the behavior of a qubit navigating a simulated CTC, and they have found that the quantum system naturally avoids paradox. The probabilities of the different outcomes of the qubit's interaction with its past self adjust themselves in such a way that no logical contradiction is ever created. It is as if the universe has a built-in probabilistic censorship mechanism. This is a stunning result. It suggests that time travel into the past may not be as logically impossible as we once thought. The quantum world, with its inherent fuzziness and its superposition of possibilities, seems to have a natural resilience to the paradoxes that would plague a classical time traveler. These experiments have also revealed something else that is equally profound, the concept of retrocausality. In these simulations, the state of the particle seems to be influenced by the measurement that will be made on it in the future. The choices of the experimenter seem to ripple backwards in time to shape the behavior of the particle in the past. This is not to say that information is being sent back in time in a controllable way. The outcome of any single measurement is still random, but the statistical correlations between the measurements show a clear and deeply strange retrocausal pattern. The future, in some subtle quantum mechanical way, seems to be reaching back to co-create the past. These advances in our ability to simulate the strange temporal dynamics of the quantum world are turning what was once pure speculation into a field of active experimental research. The notion of retrocausality, the idea that effects can precede their causes, is no longer just a philosophical curiosity. It is a concept that is being tested and explored in controlled laboratory settings. These simulations are showing that a retrocausal quantum mechanics can be fully self-consistent. The particles in these models seem to anticipate the future measurements that will be made on them, but they do so in a way that never violates the overall integrity and logical consistency of the system. This elegant, self-organizing property of quantum systems is a testament to the deep and often hidden logic that governs the universe at its most fundamental level. The role of quantum entanglement in these scenarios is crucial. When particles are entangled, their fates are linked, no matter how far apart they are in space or, perhaps, in time. This non-local connection may be the key to enforcing the self-consistency of the universe. It is as if the entangled particles are in constant, instantaneous communication, negotiating their shared reality to ensure that no paradoxes are ever created. This interconnectedness raises deep questions about the very nature of time itself. Is time an emergent property, something that arises from the deeper, more fundamental reality of the quantum state of the universe? In our everyday macroscopic world, time appears to be a linear, forward-moving arrow. But this may just be a consequence of the scale at which we operate, a statistical effect that emerges from the countless random interactions of the quantum world. At the fundamental quantum level, the distinction between past, present, and future may be far more blurry, more interconnected, and more dynamic than we can ever directly perceive. The interface between quantum computing and these deep theoretical questions is creating a new and exciting era of exploration. Companies like IBM and Google are not just building more powerful computers, they are building laboratories for probing the very foundations of reality. Their quantum processors, with their ability to handle the immense complexity of quantum simulations, are allowing researchers to explore the strange temporal landscapes of closed timelike curves and retrocausality in a way that was previously unimaginable. These simulations are exposing the limitations of our classical, intuitive understanding of time and causality. They are forcing us to confront a reality that is probabilistic, non-local, and perhaps even temporally symmetric. And in doing so, they may be providing us with the first tentative clues to a new and more unified understanding of the universe. A theory of quantum gravity that can finally reconcile the two great pillars of modern physics. The exploration of quantum time travel is more than just a quest to build a fantastical machine. It is a journey into the very heart of the quantum mystery. A journey that is challenging our deepest assumptions, expanding our intellectual horizons, and revealing a universe that is far more strange, more beautiful, and more wondrously interconnected than we have ever dared to dream.